happy to be here today and tell you about the research that we have been doing. And thank you very much, Michelle, and to the organizers for inviting me. Okay, so yeah, this talk is very much focused on the human component, so I think it's perfectly on track. And the title is Coordination and Synchronization in Complex Human Networks. I would like to start by clarifying what we mean with this term complex human networks, which is fairly new in some ways. So we call it a network because, as we all know, it's a system composed of many interacting units, so they have some kind of coupling between them. But a peculiarity here is that at least one of the units in the network is a human, which means that there are components such as emotions, relationships, agendas, sometimes hidden agendas. Sometimes maybe I like somebody, I don't like somebody else. And there's also the element of unpredictability, which means sometimes stochastic dynamics or time-varying dynamics. And we call it complex because, as with other systems, it is not uncommon that there are some collective dynamics that emerge from the interaction of the agents, and we are not typically able to infer this collective behavior just from the knowledge of the individual components. So this is what we call a complex human network. Let me acknowledge a few people who, some in our groups, some in others, have contributed to some of the works I will present. Mainly, of course, Mario, who is the head of the lab I've been working in for a lot of time, although now I'm an assistant professor at the Scuola Superiore Meridionale, which is a school for advanced studies in Naples. And then more recently, I've been working with Francesco, who's also an assistant professor, but at the University of Naples, Antonio Spallone, who is a PhD student, and Antonio Grotta and Angelo Di Porzio, who also are PhD students. I will present collaboration that we have done with them. And Benoit is in France. We are collaborating with them and many other partners in this Share Space project. I will tell you something about that. Right, so let me start with some motivation about why we would like to study these systems. And indeed, maybe for us, control theoretical people, sometimes studying humans might appear a little bit exotic or maybe out of our comfort zone, at least at the beginning for some of us at least. But it's important to study these systems. And the reason is that in many human activities, some kind of group interaction happens. Here I'm reporting examples from group rehabilitation therapy, team sports, musical performance, but also more practical applications such as manufacturing, where people have to collaborate to deliver some tasks. And an interesting fact is that in all of these examples, when there is some kind of repetitive task, an intentional or unintentional coordination can happen between the individuals. Think of, for example, of people working on an assembly line and carry out a repetitive task. Now, one interesting thing is that there is abundant literature showing that when people synchronize their behavior in repetitive tasks, they tend to report a much higher level of well-being and effectiveness in doing the tasks. And this is literature which is coming from the psychological and neuroscience field. Right, so this is something we would like people to display, so coordination and synchronization, which is something that is maybe more familiar to us. Another piece of the puzzle is that many of these activities will, at least partly, move with time onto virtual reality environments or augmented reality environments, but also environments where there are some robots working with people. And in all of these examples, a key question is, how do we design control laws and a thing that we in this field sometimes call cognitive architecture. So laws and algorithms and data sets that drive the behavior of robots or of avatars that interact with people to help them coordinate and achieve the tasks that they're performing. So this is a key question here. And indeed, several key research questions stem from these considerations. So one is concerning modeling of these systems. You already know it's pretty difficult and sometimes even not feasible to model human dynamics. But if we restrict the action to some specific cases, such as repetitive actions, we can perform some kind of model. But we have to understand which mechanisms enable such coordination I referred to. Which mathematical models describe this phenomenon? And the mathematical models that are given in the literature, are they enough to perform some kind of control, if you want? And then to perform this control, allow me the quotes, because of course we don't really want to control people in the classical sense, but we want to help them and steer the behavior to achieve some desired activities. So can we design avatars or robots or cognitive architectures that move in a human-like manner so that these avatar or robots can integrate seamlessly into the group and not be perceived as something else? Can we enhance human coordination? And can we encode information in the movement of these avatars? This is something I will not discuss in this talk today, but if you're interested in how to do that, we have a paper on that that you might look into. Which is by the way, just to tell you in a second what there is research showing that when I'm grasping something like a bottle, it is possible to convey if I'm doing that to drink it or to pour the water and so on. And you can embed this information into the movement and people are able to read it. Anyway, let's stay on coordination, which is the topic for today. I would like to tell you what is possible in terms of modeling of these phenomena. Now, this is actually something that dates back some 45 years ago at this point. And of course, people have studied coordination, both within the human body and between people. But only up to 45 years ago, the thing started becoming quantitative. And there was this scientist, Kelso, who started with this nice little experiment. You take a person and ask them to oscillate their fingers in an anti-phase manner, like this. And you ask them to do so faster and faster. And you may try this if you want at some point. The thing is that when you go faster and faster, at some point you will find it difficult to remain in anti-phase, and you will start to oscillate in phase, like this. And this phenomenon, well, that's something we are all familiar with. We call it a bifurcation. And indeed, Kelso and others in a second study with Haken and Bunce were able to model this phenomenon with a very simple nonlinear system, which is this oscillator dynamics here, which has also been reformulated in a different state-space model. So either with phases on a circle or with position and velocities of coupled systems. And this was the first time that people modeled human body coordination with nonlinear equations, with ordinary differential equations. Then the next question was, okay, but does this coordination only happen for some mechanical phenomena into the body, or can also happen between people? And to study that, Richardson and others set up this experiment where you put two people rocking on two chairs. And they are in the same room, so they can, in principle, coordinate with each other. Two kinds of instructions were given. In one of them, people were asked to rock in phase or anti-phase with each other, right? So intentionally coordinate. Whereas in the other experimental condition, people were instructed to rock at their preferred tempo, so not necessarily coordinating. At the same time, there were three conditions concerning the information that people received. So in one of them, the focal condition, people were looking at the chair of the other person. In the peripheral condition, people were looking ahead of them, so they only had partial information about what the other person was doing. And in the no information condition, they did not have any information on what the other person was doing. And Richardson and others studied whether coordination emerged in this setup. And an interesting thing that they found is that, again, the dynamics could be modeled by that same Haken-Kelso-Banz oscillator. Although now the setup is completely different because you are studying coordination between people. And when people were instructed to synchronize, they could do so both when looking at each other and when having the person only in their periphery. Whereas when they were not instructed to synchronize, they did so only when looking at each other. So even then, some kind of coordination would happen, although weaker. And so the main message here was that coordination arises from self-organizing dynamics based on attention and information rather than only anatomical or mechanical constraint. And this might seem intuitive, but it was not obvious at the time whether this was the case or not. Right. Another stepping stone in this process of studying coordination between people was with Noy and others. I don't know if you have ever practiced some theater. A nice exercise that they do sometimes is this mirror game, where you have to, okay, so here is a video example of this. So the task is to imitate one another, performing some motion which is somehow enjoyable to perform or interesting in some way. So that is a kind of game. And you can do so either with a leader and a follower or jointly improvising. And so to study this fact, this phenomenon more quantitatively, so Noy and others built this contraption here where there are two levers that two people can move. So basically they are constraining the movement to 1 degree of freedom, that is the key fact. And people had to move either in a leader-follower setup or in a jointly improvised setup. And they wanted to see what happened and quantitatively study this phenomenon. One key finding that they found was that when stopping, people would halt in as short as 40 milliseconds, which is remarkable because the reaction time for people is at least 250 milliseconds, which means that people were constructing a mental model of what the other person was doing. And then they characterized the motion in the different setup and found that, surprisingly, experts synchronize better when there is no leader, which means that maybe they are taking shared responsibility for the task. And when people play the game without a leader, they can enter that state with very low mismatch between their trajectories, so they can become very synchronized. Right. And then they also performed some modeling of this interaction, so they built some ordinary differential equations, and they put it into a system, and then had either the two copies of the system play with each other in a jointly improvised condition, or have the equations follow a recorded human trajectory to try and see if the model actually captured what people were doing. And indeed, they could do so. So, on the top, in this figure here, you see what people were doing, either in the leader-follower condition or the jointly improvised condition. And this is what the nonlinear equations did, let's say. And you might see that when coupling two avatars, if you want, they could mimic quite well the jointly improvised motion. And also when an avatar was following a pre-recorded human trajectory, they could more or less display the same kind of trajectory. So, in line of principle, they were able to replicate the behavior in this game. However, it was not perfect, as you can see, in the sense that here the precision in following the leader is not that great. So it was a step in this literature. Then a key turning point came when this pairwise interaction was extended to a group interaction. And now we are going towards the complex human network. So basically what Alderisio and others, together with Mario and Benoit Bardy, which I mentioned at the beginning, so what they did was extend this mirror game to a network scenario where people would interact in groups with different network topologies, performing this task here. The task is to oscillate one part of your body back and forth. In this case, it was a finger, with the goal to synchronize your motion with that of the others. So again, we find the pattern of restricting motion to be able to study it. And this was the task, which is called the multiplayer mirror game. So this is what they found. So first thing, they extracted a phase from the linear motion of a person. And this notion of the phase will come back again later. And they estimated a natural frequency for each participant in the group. So the frequency we tend to have when moving by our own. And then they observed, looking at people, that the level of coordination, which is measured by just a scalar number, now I'm not defining it, but I will do so later, depended on two things: how close the frequencies of the people are, and how connected the graph is. And some of you might know of a simple model which have the same characteristics, which is the Kuramoto network model, which is a very, very simple model, where each node in the network has a phase, a natural frequency, and is coupled to the other nodes in the networks via some nonlinear coupling. And indeed, Alderisio and the others verified that the kind of synchronization achieved by the Kuramoto model had the same characteristics that we found for the network of people. And so in a way, it was very surprising that the complex dynamics between people could be modeled with this simple nonlinear system. Now, just a snapshot to show that I won't describe all of the other studies, but this one is nice. They put some violinists. This is by some colleagues in Israel, and actually they made a couple of publications on mutual communications with this. They built this nice setup of violinists playing together, and they had to remain synchronized in the presence of delays which were introduced via earphones. And they wanted to see how people did to remain synchronized. And they found that people can change their speed, they can ignore other people in the earphone, which means cutting edges in the network. So, a few different strategies. And again, the dynamics could be modeled by Kuramoto network models, although with some delays to account for the delays in the earphones. Right. So, we are halfway through. The key fact up to this point is that these nonlinear oscillator models, such as the Kuramoto network model, the Haeckel-Kelso-Banz model, can be used to describe motor coordination between people, which is relevant in many applications in real life. And with these models, you can describe a plethora of phenomena. Some of them I mentioned, some of them I did not, such as unintentional and intentional coordination between two people or between a group of people, the effect of the interconnection of the topology of the graph, the presence of communication delays, frequency reduction where people are connected, or leadership emergence. There are also studies on that, which I did not discuss. So now, clearly, the next step is, which maybe is the most relevant for us, control theorists, is how do we affect the dynamics of the network to steer them towards coordination, which we know is beneficial for people. So, questions that I would like to answer are, how do we design avatars that move in a human-like manner, that coordinate with people, and that induce some specific motor behavior? And this is the second part of the talk, where I will discuss some of the things we have been doing. But first, I would just like to mention that we are not the first one attempting these tasks. Mainly what people have done until now is to design avatars that can coordinate with one person. This is what mainly the literature has been focused on. Such as, for example, building a setup where there is one person moving a finger, seeing a screen with another person moving a finger and trying to coordinate them. Although, in this case, the screen was maneuvered by a computer. Or designing avatars that can follow a leading person in the mirror game, such as what you see here. I just wanted to show you what people have done without going into the detail. And here the human is the blue one and the avatar is the green one, which is the follower. But a key fact which is missing in the available literature is that coordinating with others does not necessarily mean increasing coordination in the group. So coordinating with others is useful, for example, when working with people with disabilities, motor disabilities, trying to help them in that sense. But if you want to increase coordination in the group, you have to do something different. And so key open questions are, how can an avatar increase coordination? Are the current models sufficient for control design? Little spoilers, we believe they're not. And how do you treat complex motion, which is not just moving a finger, but maybe like moving a package from one place to another in an assembly line? How do you treat that? And this is what we're doing at the moment. This is a work I've been doing with Antonio Grotta, who is a PhD student in Naples, which is about synthesizing these avatars that can increase coordination. So we consider a group of people performing some periodic motor task. Each person is doing a movement, and we have to associate to each movement a phase on a circle. You can see that we are going towards the Kuramoto network model. And indeed, we exploited the fact that the literature has shown that this network model can be used to study interaction between people performing repetitive movement. The key assumption here is that one of the nodes in the network is actually an autonomous avatar with the goal to help people coordinate. To measure synchronization, we use a classical metric in oscillator theory, which is the order parameter, which basically is very simple. It's a number which is close to zero when phases are scattered around the circle, whereas it is close to one when the phases are close together, so they are more or less synchronized. So we want it to be high. And our control goal is to solve this optimization problem where we maximize the average of this order parameter over the whole interaction by changing the frequency of movement of the avatar. That is our control goal. And we have showed what is the best behavior when you have only two people, and for three people we have done something else. For three people or more, we have done something else. Right, so this is what we did for two people. You can define the differences in phase between two people, so theta ij is theta I minus theta j. Then you define a configuration of the network, which is the concatenation of all the phase differences, and say that the configuration is phase locked if it remains constant. So basically phases are maintaining their differences while moving on the circle. And what you can show is that if the faces of the two participants are not too different, and if the frequency of the avatar is exactly the average of them, there exists a face configuration which is face locked, so it remains constant. It maximizes the order parameter, so solves the optimization problem we are seeking, and the phase of the avatar is between those of the participant. So basically the answer is very simple actually. So the frequency of the avatar should be the average of the people's frequencies, which actually is fairly intuitive if you think about it. And you can also show that this configuration is locally asymptotically stable. However, the problem is that when the analysis involves 3 or more oscillators, I don't want to call them necessarily people in this simplification, then the analysis becomes very cumbersome because you have a lot of trigonometric functions, it becomes a mess to treat. So we thought about using reinforcement learning control to solve this optimization problem. So we started using deep Q networks as a solution to this problem, although we also then later moved to PPO, which is a more advanced state-of-the-art algorithm. So for those of you who are a bit familiar with reinforcement learning, here in this setup, the action was the avatar's frequency, and the reward is the synchronization index, which we want to maximize. Here I reported the state of the error model and the action more formally, but they are details. They're not too relevant at the moment. Concerning the training, and this is actually the annoying thing, in principle, you should have the avatar play many times with people. That would be the ideal scenario to understand what the avatar has to do. But of course you cannot do that, because you cannot take people and have them sit in a room for days playing with a computer. So what we had to do in this case was to simulate a network of people using those Kuramoto network models. And this is the numerical validation of this learned control policy. In these pictures here, you see the color is the synchronization index. So yellow means very high synchronization, and dark blue means very low synchronization. So we want yellow. On the x-axis, we have the heterogeneity in frequency of the network in which we are validating the control strategy. So basically we took a network of 5 simulated people, and in one case we had them oscillate without the controller, and in another case we added the controller on the right to see whether synchronization improved. On the y-axis we have the coupling strength in the network. And what we observed is that when adding the avatar to the network of simulated people, the range of parameters, of the network parameters in which synchronization is observed is much higher, which means that for this network here, the synchronization value grew significantly. So in principle, it seems that this control law is able to increase coordination in the group. Here there are other studies which I'll skip for the moment. Right, so now we thought we had something, and we wanted to validate that with a real network of people. So we performed some experiments with this setup, which is called Chronos. In this setup, you have an infrared sensor on which you move a hand, and this hand will be transformed into a ball on the screen, and the task, similarly to the multiplayer mirror game, is to coordinate your movement with that of the other people. That's the goal. And we considered a few experimental conditions, among them one in which you play by yourself, and another one in which you play seeing the balls of the other people, and the final one in which you play but also with the avatar into the group to see if that helps. And then some more. Yeah, I'll skip this. Right, so this is what we found, which is not ideal. In these graphs, we have 3 groups of people. you should look at the P condition, which is people only, and the CA condition, which is with the cognitive architecture into the group. And on the y-axis, we have the synchronization index, so the order parameter. And basically what we found is that the orange and yellow data, so the people only and the avatar condition, are more or less similar in all the cases, which means that when we put the avatar into the group, it doesn't worsen synchronization, but it doesn't improve it either. A nice thing is that people did not realize most of the times that they were playing with an avatar. So this excludes the possibility that people intentionally ignored the avatar because they thought it was something else. But we were wondering why we had this difference between the numerical data, which seemed very promising, and the experimental data. And so we also tried changing the reinforcement learning algorithm using PPO, which is one of the most state-of-the-art models. We tried changing the training scenario, many things, but nothing changed. So the numerical results were actually the same. And in our opinion, this means that Kuramoto model on which we trained the control policy may be sufficient for some analysis, but it's not sufficient for control. So that is the message that we are taking from these results. So now, with Angelo, another PhD student, we are trying to develop more advanced models of human behavior. A nice thing that you can see here is this. On this plot here, you see people moving their arm, and this graph is the occurrence frequency, so how many times a specific value of velocity was observed in their movement. And you might see that the distribution of velocities for a human person is very different from that of a linear oscillator in a Kuramoto model, which is already telling us that the linear oscillators are modeling something, but they are not really close to what people are doing. And also, these models, which are very simple, also neglect all of the individual peculiarities of how people move and how they interact with each other. On these graphs here, I'm reporting something which is a staple in the literature. It's called the individual motor signature, or motion signature. And basically, it is constructed by taking the distribution of velocities or of the amplitudes and plotting them on some graphs. And basically what you can see is that each person will have a distribution of points in these abstract planes showing that they have an individual way of movement. And with the Kuramoto network models, you don't capture that. So we thought, can we do that? Can we design some models that capture the individual components of motion? So we designed some personalized machine learning models to see if we could capture those dynamics. We used, again, those data from the movement of the arm from some previous experiments. We built a machine learning model based on long short-term memory networks, where basically what the model does is trying to predict the next velocity sample in the movement given a past trajectory of the movement. So this is the past trajectory. The network is predicting a velocity here, which is sampled, and then comparing with the comparison happened here with the true value of velocity in the training data. But in the end, it will generate a position value, and in this way, construct in an autoregressive manner a signal for the position. And we selected, after training, the network parameters that maximized the style closeness with each person. So we had one model for each person. And this is one of the results. The blue line is the recorded signal of a person, and the black line is the generated signal from the model. And as you can see, They are not exactly the same, which is what we want, because we want to replicate the style, but we want to be able to generate original movement for training the reinforcement learning models, and indeed we achieved that. When we look at the distribution of velocities, they are very similar. And when we look at the planes concerning style, we see that the dark points, which are the generative models, are much closer to the lighter areas, which are people's actual style, compared to the linear oscillator models, which are right here and are completely far off. And the same for these other plane of amplitudes. So now, the challenge is interconnect many of these models, create a network, and train the reinforcement learning agent on that. But that's, I can assure you, it's a very difficult task, because when you couple these models, they tend to become unstable. So that's the challenge. And this is the final thing I would like to tell you about today. A challenge in which that you face when working with these things is that, as I said, when people are performing more complex movement, like maybe dancing or performing some rehabilitation exercise, it can become difficult to extract the main features of that motion, which you can do when people are moving around. But if I'm doing an exercise of physiotherapy, what is the phase of that? How do you treat that? So this is something that we have been doing with Antonio in Naples. All of our models operate in phase. So let me define, yes, thank you. I'm almost done. So what is phase actually? I just want to clarify that phase is defined in this way. Formally, for a dynamical system with a stable limit cycle, phase is just something that grows linearly from 0 to 2 pi with a period which is the period of the limit cycle, and you can divide the state space in region where each point has a specific phase. So that's the standard idea. We had to extend that thing to pseudo-periodic signals, which are signals which are not exactly periodic, because people will never be exactly periodic in their movement. So we extended that. And how do, let me very quickly tell you how people do that in the literature. When people have to map a complicated physiotherapy exercise into a phase, what they do is apply principal component analysis, apply a Hilbert transform, and with that, compute a phase. But this is hugely problematic for two reasons. The first one is that projecting onto one dimension makes you lose too much information, and the Hilbert transform is not causal, so you cannot apply it online. So we devised our own model, which works like this. You have a signal. In this signal, you build a similarity score by extending some windows of comparison, and at some point you will see that the signal that you captured is very similar in two windows, which means that you have found the first loop in this signal. In this loop, you construct a phase from 0 to 2 pi, and for the signal at time t, you seek that in the previous loop, and with that, you find the phase which is the most similar to the point you are now. I just want to show you a couple of videos and results to show that this thing actually works without going too much into the detail. So we tested that on nonlinear chaotic systems, on human motion data. This is actually me performing the exercise and Francesco doing a more difficult movement, and on ECG electrocardiogram data. And these are the results. The purple line is the estimation from our algorithm. The green dashed line is the true benchmark, if you want, which is obtained from human inspection. And as you can see, here they are completely overlapped. For the human data and the ECG data, they are much more similar than with the other algorithms. So the orange and the red one from the literature. So, which is to say, it works. And we also apply that to physiotherapy exercises within that share space project. This is motion capture data of a person performing this is called the Superman exercise, which you can see, I mean, it's not perfect, this movement. It has a lot of noise, and the person starts to move weirdly in space, but still, we're able to estimate the face of the orange line. We're able to estimate the face quite well online in real time compared to the benchmark value. I'm now over. I'll just take one more minute to recap what I said. I've told you that in the future we expect these complex human networks to involve avatars and robots. So we would like to design avatars that can enhance coordination in these groups, because there is abundant literature telling us that this is beneficial. The mirror game and the multiplayer mirror game are paradigmatic examples to study this application. And nonlinear oscillator models are typically used to model these interactions, such as the Kuramoto model and the HKB models. There are some cognitive architectures to synchronize with people, but we are trying to do more than that. And the reason why is that currently we have found that many phenomena are not modeled. The Kuramoto model, we believe it's too simple to perform control design. And so at the moment, we are trying to design more nuanced models of motion. We are trying to design architectures that can enhance coordination and not just synchronize with people. And we are working on estimating the phase of very complex movements to make that tractable formally. This is a list of references which might be useful for reference. And thank you so much for your attention.
Great, thank you, Marco. Any questions from the audience? Yes, please, Ezra.
I think it was slide 29, the average, the one where you average frequencies.
Yeah.
Yes. Should it be plus here?
Yes, should be plus.
Okay.
Yes.
And does the simple generalization for more than two people, like you average the whole thing, not work?
Actually, so this is an interesting point. We tried that. And this is actually this graph here. So we compared the strategy learned by the reinforcement learning model with what we call the naive agent, which is what you say. So just taking the average. And we found that in many cases, this is what the agent was doing when people were face locked. But when they were not face locked, it was doing something different. So it was trying to mess up with the other oscillators to probably try and bring them into the basin of attraction of the face lock configuration. So we found some minorly improved performance for the cognitive architecture in some of the examples. Here I believe yes, here I inverted the caption. Sorry, the blue one is the reinforcement learning model, and the red one is the naive agent.
May I follow up with another question? It reminds me a bit of this. There's this famous example of cars going in a loop. I don't know if you've seen that.
Yeah.
And then an AD synchronizes them.
The one with the delay, where they show that traffic forms because of some delay, something like that?
It's like, you get these traffic waves without any control. Like people come close and then fall, and close and fall. And then if you have a single AD, it can fix it to get perfect synchronization. I don't know.
No, that's an interesting point. I didn't know about the first part, so that people form, let's say, they tend to create traffic just by changing their speed, so they become stuck. I didn't know about the control that you mentioned, so I'll look into that. Thank you.
So, very, very interesting talk. One thing that you went from the model, Kuramoto models, to describe this mechanical motion, and then you showed that model is not capturing higher order features like boredom and things like that, so the distributions are different. And then you went into designing this autoregressive networks for controlling So I was wondering if in those networks are you regularizing by this physics, which is the Kuromoto model? So at least like telling the network that motion should like look like similar to this, but then learn the higher order features as well.
Yes. So this is the model. In this case, we are not regularizing this in any way. However, that's something we actually have thought of because, as I mentioned, that when we try to interconnect many of these models, they tend to diverge. So actually, this is one thing we thought. So trying to put in some physics to give some more information to the model. And also, there's another thing I've actually been thinking about these days, is that this model here works in position, but maybe it could be maybe more clever to have it work in phase. I'm not sure about that, because that would extend more easily to complex motions. So this is some work which is ongoing. So thank you for the comment.
All right.
Yeah, so today I'm going to talk about interventions in network games, but I try to put it in some perspective for the cyber-physical human system, which is the theme of the workshop of today. So as we briefly saw in the talk of Marco, we are dealing with the cyber-physical human systems, and by definition, these cyber-physical human systems are kind of systems that bring together several layers, including the human aspect, the physical infrastructure, and the computational intelligence. And the other features that these CPHS systems typically have is that they consist of some agents, users, firms that are self-interested. And these self-interested aspects can be possibly with conflicting objectives. And what we have as a whole in this system is that we have these self-interested interactions shaped by the physics, by the infrastructure, by the communication, and so on, so that they will result into certain overall behavior of your cyber-physical system. Right. But what can go wrong, basically, is that, so we have this behavior that emerge from the self-interest aspects, but in general, these lead to inefficiencies or instabilities because there is a gap between what is desired from an individual and what is desired for the society or the group as a whole. And examples of that can be found in power system, energy systems, transportation systems, which are prime examples of cyber-physical human systems. So for instance, for energy system, a user would like to charge the EV at the time of his convenience. He wants to use the appliances as he likes. So there's this self-interest aspect, but from the overall perspective, you would like to manage the demand. You would like to trim the peak at certain hours of the day. Similarly, for transportation network, as a driver, you would like to pick the shortcuts, but as a system operator, you would like to, minimize the total travel time, for instance. Right? So there is this mismatch between this, the view of the user and the view of the entity responsible for this cyber-physical system. Okay, so this gap naturally asks for some, let's say, some actions, right? And what are the actions that I call in this talk interventions? So we need mechanism to put in place that make sure that the gap between this uncoordinated behavior and this coordinated behavior would become small. So in the sense that you to shrink the gap between self-interested and societal interested behaviors. And what are the tools that we have? There are several tools. There are taxes, subsidies, information, and so on. And you will see some of these tools later today in other talks as well. So today I will mostly think about local incentives that you can apply to the user level that to promote socially desired outcomes. Right, so that introduction was very broad, but I would like to now a little bit specialize to a class of a modeling class, and that modeling class is the so-called network games. And the motivation is that, okay, in this system we have agents that are coupled through shared resources or infrastructure, and network games actually model settings where the payoffs or the outcome of one agent depends not only on the action of himself, but also on the specific set of other agents. My favorite example is competitive multiple product markets, where you have a set of firms areas. So you can consider this a graph here. You have a set of firms areas that producing some products, differentiated products, so the products are different from each other. And what you have naturally is that you have a payoff function, which is your revenue minus cost. The revenue is xi, how much you produce, times the price that you can sell in the market, minus the cost that you have in its simplest form. It can take just a proportional form. And an interesting aspect in such market is the product substitutability, because you have multiple products. Then you can imagine that if there is a perfect replica of your product in the market, then there is a competition, the price of that your product will go down. If you have a very unique product and there is a demand for it, then it means that there's no much competition for your product in the market, and you can capture that between 0 and 1. So let's say 1 is that there is a full replica in the market, 0 it means that you have the monopoly for that product, and then you can have anything in between to capture these partial cases. If you write a demand function, what you get is that for this price, because this price is actually the only quantity that couple this agent's payoff, the rest, as you can see, depends on I, but these payoffs will have this familiar linear term, which means that the more you produce, the price will go down, because there is a certain demand for you. But then there is this interesting term that appears, this summation of this Pij exchange, this weighted sum, and it depends on this product substitutability, right? So if you have a unique product, everything else is 0, so you just have this linear term. If you have a perfect replica, then some of these terms based on the other areas will be 1, and then the price will go down. So this will naturally a network game, because now if you want to take an action, not only it depends on you, but also depends on the others. Which ones? The ones that have to some extent some similar products of yours, and this is can be captured typically by this graph, which is then these Pij elements would correspond to the adjacency or weighted adjacency matrix of that graph. Okay, so now hopefully we know what is a network game. And what's the high-level objective is that, okay, I have this my network game, these are my players or agents that are in this system. And what you would like to do, you would like to design intervention. These are these blue terms that you want to intervene in this network. And the idea is again the same. You would like to somehow ensure that this group as a whole exhibit a desired behavior. Right? So that's the focus of the talk will be how to design this control law, or will be the intervention. In this case, subsidies, taxes, and so on. And what we have is a constraint action. As an agent, your action is bound to certain feasibility constraints, and that's this calligraphic XI. You have the typically called budget constraint, which means that your intervention might not be arbitrary, but you're bound to certain budget or generalized budget constraint. For the constraint action, I assume that they are decoupled. For the constraint interventions, they can be coupled. For instance, you can capture a case where the norm of the entire intervention is less than 1, which is a coupled scenario, because you get u1 squared plus u2 squared and so on. Okay, and this is just the technical regularity assumptions on sets. Okay. Okay, now I fixed the high-level objective. I know what I want to do. Now, what I need to specify here is that what model for my users, for my agents, players I'm using. Right? So the first one is just specializing from a general utility functions to a linear quadratic form, and therefore this is sometimes called quadratic network games. And then here you see the quadratic form of qi. The linear term is xi bi. You see, at least the pointer is. Oh, okay, I show by side, and then so this I is the coupling between the actions of the layers, right? And now we are from agents actions. What you can do? Well, let's say I consider two cases. One is continuous time and discrete time. For the model-based interventions that I'm going to talk about and adaptive interventions, I use the continuous time. For the purely data-based, I will use the discrete time. The continuous time update is saying that, okay, as an agent, the xi, the action, is moving into the direction that is best for that agent. Which direction is the best is the gradient of the utility function. Right? So asymptotically, you're solving the maximizer of this. Right? That's this. For the discrete time case, I consider simply best response dynamics, which means that given the action of neighbors at time k, the best you can do is to find the maximizer of that utility function, and that would be your action at time k plus 1.
Nima,
Yeah.
could you please comment on why should the payoff function take that form?
Right. So yeah, thanks. Yeah. So this utility function. So this is at this level general, and as I said, it depends on your action and the action of a specific set of other agents. So if you, for instance, yeah. So the part that depends on your action is as linear quadratic. So it's like say half QA xi plus xi times bi. So that's just depends on your action, and then still you need to add the coupling with the other layers, and this would be, so it's like the xi times, this would be like the price function in the previous slide. So that would be, if you map it with the, for instance, previous example, this would be how this degree of substitutability appears as the price function. So that's just.
So your example fits in this.
Yeah. Yes.
I think
Yeah. Exactly. Yeah.
That's
The
the
example.
generalization of your example.
Yes, indeed. Yeah, this example.
But
Right.
it needs to be put back. It be complex.
That's the extensions, yes, right. Yeah, I will comment on that in the last slide. But this is so-called the standalone marginal cost, BI, and this is that I of x is really like the coupling, which, for instance, in this example is the degree of substitutability. In other example, can take different interpretations, but it's just the coupling that comes from the other layers as opposed to a standalone marginal cost. So you can think of standalone marginal cost and then network effect, which is this ZIFX. Okay, so now what happens is that, okay, you have this agent's behavior. Two scenarios can happen. Either these matrices are Hurwitz in a continuous time, or this guy is sure stable, or not. If not, you don't converge. If yes, you converge, so-called to the Nash equilibrium of your dynamics, nominal Nash equilibrium dynamics. There is no intervention yet. Right? So this no intervention is undesirable Nash equilibrium or lack of convergence. And now here comes the part. Now you would like to define a target profile, and you can, there's a big debate on what should be the best target action profile, but let's say for the most of the this talk, I will fix it as the one that maximizes the summation of the unregulated utility function, so-called social welfare maximizer. Okay, and the idea is that you want to now here, let's say I'm at the nominal Nash equilibrium. Can you design interventions such that you move this point to another point, and what's that point is this social vector maximizer. That's the problem formulation. Okay, so let's talk about one slide about problem feasibility. Because I define this social welfare maximizer, first I should say under what condition it exists. And there is this weak coupling condition. This P is the adjacency matrix of your network as before. And then this A was the weight of the coupling, because P is between 0 and 1. A can scale it to arbitrary number. Is less than Q. Q is this diagonal matrix coming from the quadratic term in the utility functions. So if this holds, then you have a unique social welfare maximizer, and it's necessary and sufficient in the unconstrained case because it follows from a strict concavity of the utility functions. But we need one more, and for that we need a slight preliminaries, and that's for the intervention, for the budget. You can think of if the budget is too little, you might not be able to reach that point, and if the budget is sufficiently large, you might be able to reach that point. That's the condition about that. And for that, I need a notion called variation and inequality, which means that you find a point x bar in your feasible set such that this inner product is non-negative for all the points in the feasible set. So there is a big literature on what is variation and inequality, how do you solve it, and so on. But I just need it for this existence of, for this feasibility constraint. And now I use SOL to denote the set of solutions to this variation and inequality. And now from the equilibrium perspective, what happens is that if I do nothing, I'm looking at the Nash equilibrium, which is a solution to this variation and inequality. If I take the continuous time, this F has this explicit form. The effect of U is simply modifying this F by a constant U bar, right? So that's the effect of intervention, which provides this budget condition, meaning that XO, your social welfare maximizer, where you want to end up, should be a solution of this modified variation and inequality. So you should be able to modify this map F such that XO belongs to this solution. And just if you don't want the technicalities of this, as a simple case, so let's say there is no constraint on the action. So X is Rn, Q is identity. And then you get a term like this, very explicit, that you see network parameters, AP, and the B is the standalone marginal cost. This vector should be in the budget set, right? And you can imagine that if the budget set is bigger, it can contain this vector, and this is feasible. If it's too small in some directions, it may not be feasible. So, but this would be the budget condition, and the weekend coupling condition of the on top. Right. So the side remark is that this condition also ensures that the uncontrolled system is stable. So the uncontrolled system will converge to the Nash equilibrium. That's also a sufficient condition for that. Okay, now I want to highlight the critical role of available information to give you the solution to this intervention problem. So if I ask what is the solution to, what is the proper intervention to relocate the Nash equilibrium to this social welfare maximizer, the type of solution depends on what you know as the system planner, and that's crucial in constructing the system. And for that, to recognize this role, we distinguish several scenarios. First scenario is the complete information scenario. So you know everything about the network, you know how the adjacency matrix is, you know what are the standalone marginal costs, and so on. The second scenario is that you know exactly where is the social welfare maximizer. Okay? You know that point. The third scenario is that you can envision is that you know the network, so you know how the coupling between the utility functions work, but you don't know the parameters of the utility function. And the fourth one is that you know only the standalone marginal cost, VI, but you know nothing about the network. And the fifth one, which has a slightly different twist, this is that you don't know anything about the utility function network, anything, but you know a bunch of data samples that is coming from the history of these signals applied. So you look in the past, people have applied this intervention and that intervention, there was this corresponding action, so you collect them as a set of database, and that would be the fifth scenario that I will discuss today. Yeah. So then this will be a slightly modified problem formulation. The problem is exactly the same as before. The only change is the blue part. So as I said, the solution should be tailored according to the set of information available to the agents. Right. So let's start with the one that has the complete information. right? So which means that you know the network, you know the utility functions and so on. And I write this for simplicity for Q equal to identity for simplicity. And as you can see here, we have complete information. Then you can compute the social welfare maximizer explicitly, right? This is X opt. And then you can plug an explicit form of I minus AB X opt minus B into the agent's dynamics. And what happens is that this appears as a reference signal. So if you just plug in this expression to that, it's like that you are tracking X opt, which means that asymptotically you will get what you like. Okay? So that's the open loop control is sufficient when you have complete information which matches our intuition from control theory. If you have constraint actions and interventions, so this is without constraint. If you have constraint, you cannot explicitly write it like that, but first you should find the social welfare maximizer from the convex optimization problem that you have, because you want to maximize the total utility function and subject to some constraint, and that's convex, so you can solve that. But then in order to find the best intervention, you need to solve this variation on inequalities. So X opt is given, can be solved. You just find a point U opt that satisfies this variation of inequality, and you set it again. It is still open loop, it's just that you need to solve a variation of inequality. So this was the case for complete information. The second case was that I know where I want to end up. I know the social welfare maximizer based on the application, based on prior knowledge, whatever. I know that target profile. In that case, simply in the unconstrained case, you can, again, in line with control theory, you can apply integral action to create an error, compare the action with this reference, and penalize it in your intervention. If you have constraint, you can do the same, but you need to properly project it in the budget constraint, so it will be a projected integral control. Okay. Now I go to the third scenario, and that is when I know the network information, so AP, but I don't know the other parameters of the utility functions. In that case, you can resort to a static state feedback, which will modify this vector, here, such that asymptotically the social welfare maximizer can be achieved, right? So the idea is that if you write an algorithm for computing computing social welfare maximizer, then you will see that you need some terms to correct for it in the vector field of the action dynamics, and this APTX, that's the exact term that you should that can correct this nominal Nash equilibrium vector field to the social welfare one. So that's exactly the mismatch. This P transpose will balance the game, and then you can end up in the social welfare maximizer. Okay, as usual, if you have constraint case, things get a bit more complicated, but nevertheless can be done. We need a slightly stronger condition than the feasibility that we saw before. So for feasibility, this is less than 1. Here we need less than half in the undirected, and here then we need to project this again, this state feedback to the budget set U. Right, so that's the only difference. And the fourth scenario is that you only know the standalone marginal cost of the agents. You don't know anything about the network. And there it gets quite complicated. And so even the standard adaptive control, typically you have a reference signal. Here we don't have. But here is the idea. So we know how to deal with this case. So if somehow I manage to asymptotically mimic this case, then I'm good. Right? So the idea of this seemingly complicated, well, it is complicated, adaptive control-like policy is to asymptotically construct the third scenario. So in fact, this KTX will asymptotically go to APTX. and these dynamics are make sure that this construction is possible, and these are mostly technical. This mimics the action dynamics of the agents. This makes sure that the actions will not grow unbounded, and this is just a cross-term correcting for the Lyapunov analysis. But again, the message is that with this pseudo-adaptive control, with only knowing B, you can relocate the Nash asymptotically to the social welfare maximizer. Okay. How much time I have? Just 20.
25.
Okay.
Can I ask a question?
Yeah, sure. Yeah.
So I didn't understand the setup. So there is a planner and then the agents. The planner sets the incentive and the agents respond to that, and the assumption is that they will play a Nash equilibrium strategy.
Right.
But then the dynamics that you're writing are time quest response. That's the gameplay between the agents. But now the incentive is not set prior to that. The incentive is changing with their dynamics.
The incentive is updated with time, at least.
Yes.
Right? And sometimes that law is fixed, like a state feedback which is
Yeah. So I
fixed.
mean, if you see like from the planner's perspective, it's a one-shot stack over game. So they set the incentive and then they respond by Nash equilibrium. But the thing is, how do they converge to Nash equilibrium? So the dynamics is kind of saying that they will eventually converge to Nash equilibrium. But then it's not like repeated Stackelberg game between the planner and the agents. Like
It's not also one time, so it's not that you apply an incentive and then your hands off. That's not like that. So when you think of even this dynamics, is like that there is certain update. So you're okay. This is continuous time, so it's a bit difficult to time t+1 and so on. Maybe in the discrete time will be more clear, but that's immediately. So when you apply this incentive at time t, then this is obtained from this dynamics. Okay, you determine the incentive at time t, but then the player are playing this kind of pseudo-gradient dynamics, right? So it's in continuous time. If you discretize it, you can think of at time t you apply, and they react, and immediately you have to apply again and you react. But this is in real time.
It's some kind of like it's a continuous.
Yeah, it's a continuous.
And like you're steering them to some.
Right, it's a like continuous action indeed. Yeah, there.
I'm just looking at equation 4b, and it reminds me of a piece of literature that goes back to the 80s and 90s.
Reminds you of?
A piece of literature
Okay.
on reverse Stackelberg games. Reverse Stackelberg games. The leader designs an incentive group as a function of the followers' actions. And they come up also with an interesting geometric interpretation in terms of separation principle. So you take the social optimum, you look at the surface level of the followers, and you make sure that the incentive group makes the payoff moves along the tangent. So I'm wondering whether, and you can design matrix K using this separation principle. I'm wondering whether there's any connection or there might be some interpretation in that sense.
Yeah, I think to answer that, I need to exactly look at that piece of literature that you're referring, but it sounds intriguing. If that's a real time, so it's a repetitive action.
So it has the same structure that you're presenting.
Okay, I have to look at that, and we'll be happy to look at it.
Okay.
Thanks for mentioning this. Any other? If you have questions for the model-based intervention, but adaptive is between model-based and database, so it's like learning the control. But if you have other questions, I can answer. Okay. So if not, I move to the database interventions and some introduction to this. What do I mean by this, and what kind of approach I'm using here is that, okay, if you see the picture, this is a classical picture that is for, should be familiar for a control engineer, for control theorist. And there you have a plant. You collect data from the system, and typically what you do is that from that data, you model your system via this celebrated field of system identification. And once you have that model, then you design a controller that is tailored to that model, and then you plug it back to the plant. Right? in the recent, like last 5-6 years, there is this massive trend and plethora of papers. Now I think it should be updated daily. There's thousands of papers on this direct data-driven control idea, which means that you're bypassing the system identification step and go directly from data. So you want to go from data directly to the controller design without an explicit identification step. Right? So you will have convex program or LMI semi-definite programs that map directly data for your controller to control. And notable instance, the most sensible problem that you can think of is that you have a linear system. You want to design a control, you have data from that system. Well, you could identify the system, maybe finding least square and so on, and then try to find a controller, but there is this trend to have bypass this system identification and give you some design criteria, mostly in the form of convex programs, semi-definite programs, that can compute directly K from the data from the data collected by the system. And there is this celebrated paper developed in our group that address this same problem, as I was saying, this solving a purely database LMI. Okay, now back to the context that I was talking about. Now here, for this part of my I will talk about discrete time. Then for discrete time, as I say, that you take this best response dynamics. So given the actions of the neighbors, at time k, you find what's the best action for time k plus 1. And then compactly for linear quadratic, again, you can write it in this form where you have q and b, the parameters of the user agents. And then you have the p is the adjacency matrix. It comes from the network, okay? So we have this mix of both. Again, in the previous part, maybe for continuous time, or I did it with model-based, but here now the problem is as follows. You are given a socially desired profile. Here, I don't pin it to social welfare maximizer. You are given a reference x star, and that's where you want to end up with, okay? It's not necessarily a social welfare maximizer. And then what you're also given is a historical action intervention data samples. So there are this batch of data available to you that says, okay, under this action, this was, under this intervention, this was the action, under this intervention, that was the action, and so on. So there is this batch of data available to you, but you do not know a priori Q, P, and B. You do not know any of them. Okay, so how do we approach this problem? So let's pretend that we want to solve this in a model-based fashion for a second. And there you could say, okay, I will form a PI control, right? So I have the reference, so I just create this error, and I need to design my proportional and integral gain such that I will end up from one point, the equilibrium of the system, to a reference point of the modified system. Okay. So the problem is how to design the gains kx and k psi from the data such that the closed loop system is stable. Once it's stable, I'm guaranteed that x goes to x star. Okay, at the top is just some notation. So basically a sequence of inputs, which we are a sequence of your interventions, and xi of j is a sequence of the actions, but these are data. That's why there is an index D. So these are the data is available to you at the time that you want to design, right? And these are, don't mind the exact expression, I just provide it for completeness. The only thing to know is that these three matrices can be constructed from this batch of data that is available to you and the reference x star. So it only depends on the reference x star and the batch of data that's available to you. And the result says you solve an LMI condition in terms of theta. These are linear because E0, E1 are data, right? And then if you find this theta, then you plug it in this expression, and it gives you the P and I control gain that guarantees that the closed loop system is stable meaning the action profile will converge to X star. And one can show that, of course, every LMI that is posed, one always wonder when this LMI is feasible. And the answer is that such data exists if the incremental in data, u d k plus 1 minus u t, in this capital T is your length of data samples, is persistent, so-called persistence exciting of order 2n plus 1. Okay? So 2n is the number of players, so it's proportional to the number of players or agents in your network. Right. Just a sketch of where this LMI is coming from is that if I write a closed loop system, which means that you have your game, you have your agents, and you just interconnect it with your PI dynamics. That's your closed loop system. And you do some change of variables. So you define VK as the incremental input, you define EK as this. You obtain in some new coordinate a familiar LTI system, which the only design variable is K. Right? So by some transformation, you can get to this point, right? And then we have the result in the literature that if I have data of this system, I can design the controller. Now there is only one catch. I don't have immediately the data of this system. I have the data XD and UD for the open loop system. But this can be patched because I know part of my A matrix, so I somehow can, it's like as if I have the digital twin of this part of this state, so I can generate the data that I would like to patch this gap. Okay. And once I have data for this system, then I just apply the existing results. And I have one slide on the budget case. The situation gets a bit more complex. So the budget constraint case is that you would like to have intervention within certain budget. So you have some budget for intervention between, let's say, U min and U max, which is probably the most sensible type of budget constraint you can have. And then there is a feasibility condition. It's just that should satisfy. It's kind of necessary. And the modifications are in the blue. So instead of PI, you will add a saturation function to make sure that you respect your budget constraint. And with respect to the previous slide, all the blue terms are new. So these black ones were there. Now your LMI is enlarged, and there is a new LMI that is added, where rho I depends on the budget. If there is no budget, rho I can be extremely big. So this LMI is trivially satisfied. You can drop it, and then you can make the selection in a way that these blue terms are gone too. But if you have the budget, then this restricts, of course, with respect to the previous slide. And again, you can do the selection based on the solution of this LMI. Okay. So there are two remarks in the that I would like to add in the budget constraint case. One is that since you introduced the saturation, then you're dealing with a nonlinear system. You can talk about this region of attraction. And the region of attraction can be given by an ellipsoid that are parameterized in terms of E0 theta bar inverse. So if I look at here, you will see E0 theta bar, and so on. So if you want to ensure sufficiently big region of attraction, then you could add a constraint like this and then try to maximize eta, which means that E0 theta gets big, then this one gets a small, the ellipsoid gets big. Right? So this is just to ensure that the region of attraction gets bigger as much as possible, subject to the feasibility. Right, again we have the feasibility result in terms of persistent excitation. Still it would be 2 times n, even in the budget constraint case, so the feasibility remains similar, only the proof of feasibility is more involved. And I think I'm ready for one slide of summary and one slide of outlook. So we discussed how to intervene in a system of agents to relocate the Nash equilibrium to social optimal. We talked about the critical role of available information and then going from open loop, static, and adaptive protocols. So in this CDC paper, for the dissertation of the PhD students, Ranch Academy, you can find the result without constraints, so that you can just get the high-level idea. For constraint actions and interventions, then you can look at the journal version. Then naturally, there is some added technicality due to this variation on inequalities. And the database intervention that I talked recently is just recently published in LCSS. You can find an extended version in archive where there are proofs for consistency, exciting, the feasibility, and so on. Okay, some outlook. Well, as a system planner, you might not know the user model, so I would perceive this as crucial in designing any suitable intervention or incentive design and all that, and I think that should be taken into account, which calls for, okay, we had one adaptive scenario that could be a starting point, but in general, let's say we want to have this model-free or even online approaches where the incentive can, in an online fashion, adapt such that it can compensate for the lack of planner insight into the user preferences models. For instance, think of transportation network. I mean, there is lots of literature on what is the routing dynamics, but might not be completely accurately representing the way that the drivers opt for their path preferences. And connected to this, from the user side, there's always a notion of privacy because there's a human element in cyber-physical human system, and you might want to take them explicitly into account to make sure that privacy of the users participating in such schemes are preserved. So these are just samples of the works that we have been doing in our group on this topic. The third one that I would like to emphasize is that now I talk more on the monetary incentives. You can think of this intervention that models here were more the tax and incentives, but information is a valuable tool. You can have information as a tool to shape this behavior of self-interested agents. There are prime examples of that in transportation networks. And here there's a work by a St. J.C. student that we use ideas from nudge theory in behavioral economics to nudge these users without monetary incentives. There will be also a talk in the afternoon that you will give on karma. So I think that you might talk more about these non-monetary incentives. And partially also related to that is fairness. I didn't talk much about fairness, but for instance, what we did here is that instead of looking at natural equilibrium, which is the competitive equilibrium of the system, you might want to think about fairness as well. And then the idea that we did here is that you have both competition and cooperation, which is a fascinating phenomenon that you do not think binary that either is cooperative or competitive, but you can think at some level the agents are cooperative and another level they are competitive. And for instance, here the agents will they compete with each other, but they collaborate for an objective to bring the price below a certain threshold, which we call the socially acceptable price, and that requires some collaboration to modify the utility functions, and beyond that you remain competitive. And I think this interface between competition and cooperation is interesting and fertile domain. Yeah, with these remarks I would like to conclude the talk. Thank you.
All right, I'm looking at the time. We have 3 minutes to the break, so we have time for 1 or 2 questions. Yes, please.
So thank you very much for the talk. So one question I had about the data-driven approach, how do you account for different assumptions in the model? For example, the one about the information that is available to users. How do you account?
Information available to user or system planner?
To agents, yeah.
Agents, yeah. Yeah, so here, from the agent side, yeah, so then it means that at time K, you have information of, for instance, you know what products or how much are produced at this time, and then you make your plan for the next time step based on that. So that kind of information, for instance, in bidding markets, you bid in the 15 minutes time slot, so these results are published, right? So you know what all the agents are presumably producing, and that will be your baseline to determine what you want to bid or what you want to produce in the next 15 minutes. So that's roughly the idea. So at time K, you know what is going on, but you decide, every agent decide based on that information for the K+1 time step. Yeah.
Maybe I could reformulate a bit my question, because the part of the model-based approach, you talked about several schemes of information.
Right,
so
right.
I was wondering if that is the same thing.
I understand. No, so here you need two things. One is X star, which is the reference signal, but you don't know you don't need to know anything from the network and anything from the utility parameters, right? You don't know. You don't need to know, but you have a data, right? So it means that you could still go, in principle, go via identification, try to model the system. Of course, if there is noise, then you might not be able to modify exactly, then things get more complicated. But this can be extended with noise. We have done it a bit. But if you go via the data pass, then you don't just bypass that step. So you have the data as a proxy for your model. You don't know a priori what is Q, what is B, and what are all the other parameters.
So I'll try to skip maybe the motivation and go to the main core of the talk. So today we are going to talk. I'm going to talk about a framework I call flexible optimization, and the idea, the really core idea, is to give a human a choice between possible solutions that a system designer will compute, so that the humans can give us feedback of what is suitable for them and what they think is more optimal. Okay, so that's what we're going to talk about. So in that sense, I really think about model system as having humans in the loop, and with that, so my question was how we can optimize those systems. Think about smart grids or traffic networks by still allowing some choice be made by humans, right? So I would like to avoid the future where system designers or your smartphones or your domotic system in your home will impose me some optimal solution. I don't know how they are computed. Okay, so I wouldn't like my shower to be at the optimal temperature, or when I have to plug my electrical vehicles, I have to plug it exactly at a specific time. I would like to avoid that, and therefore I want to embed in the system we design some flexibility. Flexibility meaning, okay, the temperature of your shower can be between this value, I'm okay, and etc. Right? So the preferred route to go home should be this or that, and I'm okay with that. Okay? So how do we do that? How do we embed this flexibility in a mathematical sound way? Is not trivial at all. I will show you a couple of possibilities. There is many more to be explored, but I think we should, as engineers, think a little bit more about the flexibility we can allow the human to have. Okay, that's what we said. So the context, I spent a little time on the literature so that I want to put together a little bit the context. So it comes from very different angles. So if you look at the control literature, this is a paper appeared in 2019 looking at how we can have control signals that are not just signals, just one dimensional, right? Or a vector, what you say. Would be set, right? So you would like to have a certain set of control, and then the human will pick something that is suitable, and you would like the closed loop system to be still stable, right? So this is an interesting paper, and I take inspiration from that. There is a different angle coming from robust optimization. We'll see that some of the techniques that we are proposing here, they will go towards robustness or robust optimization. This is quite, I mean, it sounds straightforward or quite direct, right? So you would like to include some flexibility, and you still want to allow some optimality. So you say, okay, you could imagine humans to be noise, and then you want to be robust against it, right? So this is why the robust optimization comes into play. But then there is something a little bit more sophisticated in that. And the ML literature, especially optimization and ML, so machine learning literature, give a big hand because they study things like performative prediction or like stochastic optimization with decision-dependent distributions. We'll talk about it a little bit more about this, but this is something that is quite interesting and will come into play in the framework. And finally, just to give a hand to some related things, especially if you look at distributionally robust optimization, there is something that is related to that. Okay, this is a big context. It comes from very different angles. Okay, so how do we model things? How do we set up the optimization problem? How do we model things? So let's start with the optimization problem very general, right? So you want to minimize a certain cost, F. You assume it will be convex or something that it's nice to you, all right? And then you have a certain set, right? So you want to pick a decision in a certain set, and the set can be convex as well, right? So that's right. And you can model the set as a collection of inequality. This will be convenient to us. And we want, so the real aim now, we have this problem that can stem from many things like transportation, energy, etc. We want to modify it, right, such that the solution of it is not only a vector that you give to me, but it's going to be an optimal set, so a set, not a single vector, that you want to give to the user. So you can imagine that this X will give to different users, and they can choose, so that they can choose their own optimal solution independently from each other. Okay? Even though the solutions, this X is coupled here, right, you would like to give the part that is belonging to the different users, such that independently they can choose what is optimal to them. Okay, so let's have a visual. So this is a two-dimensional visual. You have two variables that you are optimizing over. This is the set. And instead of giving the optimal decision and tell the user, you do this, and that's it, right? You don't have the choice. You want to give the optimal decision, but also like some flexibility of it, right? So for instance, for user 1, you want to give this line as optimal set, and for system 2, you want to give, so the user 2, you want to give this as the optimal set. And this is an hyperbox that stays inside the feasibility region. So whatever user 2 chooses, or whatever user 1 chooses, you're still in the feasibility region. Okay, so you stay feasible. So this is the setting. I want to construct not only the optimal solution as a vector, but I want to construct this set so that I can give to the user their coordinate-wise independent set to pick from. Okay? So this is the intuition, but we have to build it, right? So this is the intuition, and now the idea is to build this set, right? To write down this set, and then modify the optimization problem by allowing the fact that the users can pick anything in this set. Okay, so how do we do that? So this is a little bit of math. You just introduce some uncertainty variable, the z, that can be anything between -1 and 1. So I'm transversing or spanning this hyperbox, and then right. And then let me go to the next slide. Yes, that's what is interesting. So I'm writing the hyperbox. So anything within this hyperbox has this linear form, where you have z, which is the uncertainty, the fact that the user can pick anything inside this hyperbox, and this represents just a reformulation of the axis. Right? So this is just this b will be a linear y, and a will be linear y, and this z transverse this hyperbox. Okay, the rest is not so interesting. Okay, so you see. So at the end, in that sense, now the constraints, forget about the cost for a moment. The constraint will be, instead of h of x, will the h of this expression will now depend on z, right? Z is the decision of the user, can be anything within this -1 and 1. Okay? And then the constraints, fine, you have the original constraint f, and now you can add or not, that's up to you, the fact that you want to allow more or less flexibility. BI measure how much they're allowed, how wide, in fact, is this hyperbox. So if you have a W that is very big, then it means that you allow more flexibility. If W is very small, then you allow for little flexibility. If it's 0, clearly there is no flexibility at all. And right, and this phi is also another modeling tool. You can say, okay, if you have phi just a minus, then you maximize the flexibility for the user. Otherwise, you trade off between flexibility and system performance. Fine, that's just standard. The interesting part now is really spanning the whole hyperbox in an independent way that leads to this robust optimization problem, right? You're trying to minimize certain costs subject to uncertain, in fact, constraint. Okay? And when you are done, when you can solve it, admit you can solve this optimization problem. Now is in y, the axis and the flexibility beta. So admit that you can solve that. Then you can, since it decouples, right, you can give to the user each their own xi minus beta I and xi plus beta I. Right? So we are assuming this x to be monodimensional. You can extend it to more dimension with quite ease, and then you can add also all sorts of other constraints, meaning if user I do something, user J will have to do something, etc. Right? So some couple preferences, you can add that. But for the ease of notation and simplicity, let's leave it like that. Okay, so each user has a scalar decision, and that's basically on his line. They are allowed to pick anything within this set. Okay, so this means that you can give the set to the user, and then they can decide their optimal decision independently of other users. Okay, this is kind of a one-shot type of thing, right? So the system designer designed very carefully this f, the constraint, and then they solve the problem, give to the user the set, and the user does what they want. All right, and that's all. That's what that's a one-shot type of thing. It relies on the fact that we have to be able to solve this problem. Right? This P2D, deterministic in that sense. This is quite a hard problem to solve. It's a robust optimization problem, which is quite hard. Okay. All right, so that's fine. So as I said, this is an NPR problem, even though at the beginning f was convex, because of the fact that you're searching for every possible z, all right, inside this -1 and 1. Okay. However, if you're familiar with the robust optimization literature, some convex approximation and reformulation procedure exist that can tackle this problem, right? So typically offer worst case guarantees. So they reformulate the problem looking at the worst case scenario. So instead of enumerating all the possibilities, they really look at some convex reformulations. And nowadays we have very general procedure. So depending on which f you have and which h you have, so if I go back, so depending on which f you have, is that quadratic, is that linear or other things, or h, is that a linear constraint, or affine, they're quadratic, etc. Depending on which constraint and cost you have typically toolboxes or a set of tools in general to reformulate the problem into a worst case scenario, a little bit conservative convex optimization problem that you can solve. Okay, so the the first look at the flexibility problem allow us to write a robust optimization problem that typically with a little bit of conservatism we should be able to solve. However, we may not be very satisfied with that. Okay, so we are thinking about what can we do next. Right? We want to refine the model. Right? We want to have some interaction with the users. Right? So these are not one-shot type of systems. We want to give the user a choice. The user pick a choice. We want to have some interaction so we can refine the model. Okay. So in that sense, to refine this robust model, and this interesting part, we assume that the user giving a certain optimal decision and allowed variation. So I'm giving the set to the users, right? This minus x minus beta, x plus beta, right? They pick a certain variable in this optimal set with a certain probability. Okay, so we assume that the user have their own mind, whatever that may be, and he goes with a certain probability law. So given a certain set, they pick a decision based on their probability. Okay, and this makes sense. In general, users they try to be rational, so they're trying to maximize something, and that depends on something that they have. So it makes sense that given a certain input, they will produce an output with a certain probability distribution. And this is what we model. So we introduce a non-negative scalar, whatever, and then instead of having here for every x, we model the constraint that we have as a chance constraint, right? So what it says? That says that now the probability of these constraints to be violated, we want it to be less or equal to delta. So we want the user to pick their choices, fine, and we want at the end the constraint violation to be less in probability less than delta that we picked, and the probability distribution depends on the decision. Right? Given a certain decision, the user pick a z, which means a point in their set, and we want this chance constraint that depends on this probability to be less than that. Okay. All right. So the interesting part here is now this distribution that depends on the decision. This decision dependent distribution is not completely independent. It's not given by. It's not exogenous, right? It's not something coming from somewhere else. No, it depends really. It's locked on the distribution. It's locked on the decision that you give. Good. Now, okay, so this is a chance constraint. We can reformulate it. We don't like chance constraint. We can reformulate it as an expectation, which it's easier to deal with. All right, and for that you can use some standard reformulations. We use a bound, the Chernow's bound. You can use others. Here we need some smoothness, so we use that bound. It's not the super tight. We can use something else. Just to say that this chance constraint depends on sort of probability distribution. You can reformulate it in a conservative way with the expected value, right? Involving some exponent, etc. Right? So, but this is the important part is now instead of a probability distribution, you have the expectations over this decision-dependent distribution of this constraint here, which stays which may be ugly, but it stays. It's fine, right? And in this particular way, we can write the problem as you're minimizing your cost, and here you have the cost plus the flexibility parameter, subject to the feasibility area. So the constraints now is this expectation value over the number of constraints that you have. Okay? And here the idea is the same as before. If we were able to solve this problem, right, we give to the user this set, and the idea is that they will pick an optimal solution for them independently of each other, such that in the expectation that constraints will be satisfied. Okay? Right, so fine. The constraints are not convex in Y. They would be convex in Y if this would be static. But now, since it's depending on the distribution Y, these constraints are not convex in Y. Okay, not very surprising. Okay, finally, for the modeling, we need its minimax formulation. This is a constraint problem. We can write it as a minimax, introducing Lagrangian multipliers. Okay, so you're minimizing over the decision and maximizing over the Lagrangian multipliers. And you add it over here, fine. Okay, so you embed it in the cost. And now you try to, right. So this is at the end what you're trying to solve. A min max over, so you mean over Y, you max over the Lagrangian multiplier, over a cost, over, yes, this cost that depends on the distribution. Right? So it's a decision-dependent distribution. I want to stop here for a moment, just to think a little bit about it and discuss a little bit about that. So, again, if the distribution did not depend on Y, on the decision, that would be a standard stochastic optimization problem. You run off your favorite optimization problem like gradient descent, stochastic gradient descent, or proximal, or primal dual, and you have all the guarantees that you want. Now the fact that the distribution depends on the decision I'm giving to the user change completely the way we approach the problem. Instead of using those type of tools, we need to use other tools. And we can take from machine learning literature, optimization in general, some techniques that are emerging, looking at the decision-dependent distribution. Right? So if you look at the literature in machine learning, they are quite realizing that that the decision they make affect how people react to it, or the users, or whatever. The system is not in open loop, basically, right? So there is a closed loop effect that they have to model, and one way to model it is with this decision-dependent distribution, right? So the decision, the thing that I tell you will affect how you will behave. Yeah?
Isn't it similar to like Nash equilibrium? It's a fixed point rather than...
So you can implement, you can think about it as a game.
Min-max.
You can think about it as a game. And we may want to go there in that way, right? So, but at this point, I'm not assuming that the users are rational or anything. I'm just assuming that they have a distribution that depends on the what they ought to pick. That depends on the decision I'm giving them, right? And I don't want to at this very moment. I don't want to go in that if I don't need to, right? So, but that's possible, right? So it makes sense that the users have a preference given the decision, because it makes sense, right? So if I tell you the temperature of your shower should be, I don't know what is you're comfortable with, but say it's 35 plus or minus 2, you say, okay, it's fine. If I tell you, I don't touch the knob, that's all right. If I tell you the temperature of your shower should be 18 plus or minus 2, then you put it at 20, and then it goes on, right? But I'm not modeling the rationality yet, right? Okay, but I'll coming back to that. Okay, so yeah, so it's if you look at the literature, some papers call it performative prediction. I don't know exactly why, but that's what they call it as well. So this is technically is a stochastic saddle point problem with decision-dependent distribution. It's in general non-convex and completely intractable because we need the characterization of D that we don't have, because it depends on the distribution and we don't, right? So we don't want to assume that we have such a thing, right? So what we do instead is that to try to solve this particular problem is that we search for equilibrium points. Right? So we search for equilibrium points, meaning we search for a y bar and a lambda bar that satisfies this equation. Right? So we'll be stable with respect to the distribution they induce. This is not the optimal point. Right? This will be an equilibrium point. Okay, so those are easier to work with, and then there is some theory about how you go from there to there. Yeah.
Isn't this the Nash equilibrium? I think that the equilibrium.
Right. We don't know those things, right? We don't know those things. Yeah.
Like Nash equilibrium under some
Right.
complete
Right.
information.
Right. Okay, so so this is what we are after. This is what we would like to do. We cannot do it. This is what we are after now. And how do we solve this is the next few slides. To solve this, we need some blanket assumption, something that we are comfortable with, that can be extended, etc. But let me go through it. So we say, okay, the function phi will be continuously differentiable, fine. Uniformly for every z, that these are the decisions that the user take, and then we think we impose strong convexity and strong concavity for y and lambda for all z. Again, we may want to extend that, but let's see in this nice setting what we can achieve. And then we have some smoothness condition, fine, all right. And then, so the first two are quite standard in the sense they just allow easy calculations for now. The interesting part will be this part, is that the distribution amount is D. We don't know it. We don't know what it is, fine. But we assume that it's sufficiently smooth. And sufficiently smooth with respect to a certain metric, the Wasserstein metric. Okay, so what it means is that if you change a little bit the y, right, all in this metric, so if you change a little bit the y, this will be an upper bound of how this metric changes the two distributions. Right? All right, so this is the extra bit that comes into play. Okay, with this assumption in place, the distance between the equilibrium points and the optimal points of the original problem is upper bounded by some constant, right? So solving for the equilibrium point is a proxy for finding good approximate saddle points. Okay, so this motivates, under this assumption, I can motivate the fact that searching for the equilibrium point is a good proxy of solving the original stochastic saddle point problem. Okay, very good. And then if you allow some extra constant value dependence, right? So for this epsilon L divided by mu less than 1, then you can say that the equilibrium point is actually unique. And to find such unique equilibrium point, we can use a stochastic primal dual method. Okay, so let's look at this, what it means. It means that given a certain yk, you pick a certain z depending on the distribution, which we don't need to know. This can be done at the user level, right? And then at the system level, I'm going to update my y, I'm going to update the lambda, and again. Right? So this is the projection operator, and then it's a standard primal dual method. Okay, what it means here is, if I look at it, I can give you some theory, but let's look at the algorithm first. So here we have something that is a little bit less conservative, right? So we did a step towards the users. We say they have a certain distribution. I don't know what it is, but it's not just, they cannot just pick anything, right? So they can pick something according to some distribution. All right, very good. And I am also introduced the fact that they can participate, right? So by setting up a primal dual method, now I'm doing something from the system perspective. I'm trying to optimize my variables. and I ask their feedback in a way, right? So I optimize something, I tell them, okay, now you pick whatever Z you want, and they pick, and then you go on. Okay? So there is more interaction, less conservatism. I'll tell you a little bit more how this is converging in a slide. But now we already know that we already know that this cannot work, right? This cannot be practically working, right? You cannot ask the user for this to converge, I don't know how many times if the temperature in the shower is good, right? So that's practically, that cannot go, right? I don't know you, but if I'm asked already twice, I will be okay. So, okay, so if I tell you a little bit the theorem, fine, okay, under some assumptions, then I can choose a step size. This is quite, I would say, standard if you know the theory behind. You choose a certain step size, then the primal dual will generate a sequence that converge in this particular way, right? So you converge to the equilibrium point up to some error that depends, in fact, of how these expectations look like, right? So this is stochastic optimization. This should be quite standard, right? So in that sense, it means I can make the algorithm converge arbitrarily close to an equilibrium point, which is close to the stochastic thing. So I'm quite happy. The user will hate me, but I'm happy I optimize the system. So how do we make the user not be unhappy? Right. Right. So this is it. So I want to give, I will not give a lot of details, but I want to spend a couple of minutes discussing this. So in the accompanying paper, there is a middle ground. And the middle ground goes towards the direction that were mentioned. So instead of giving a user, instead of us approximating the user as a totally mindless person that takes a distribution that we don't know, we can think of modeling such a user a little bit more and saying, well, the users respond in some mechanism. For instance, we have a model for the user distribution, okay? Or we have a model for the user distribution up to a certain error, okay? So if we have, if we know that the users are behaving as rational people, right, you can imagine that to estimate, depending on some inputs, their best response mechanism. Okay, so imagine that they are solving an optimization problem themselves. To know what to pick, you can, given some inputs, you can infer what's the best response mechanism they have and model it as a distribution. Okay, that's possible. In that sense, you will commit an error. There will be a mismatch between the actual distribution that you think they have and the thing that they do. So there is going to be a little mismatch. And if you do the math, then the conversion of this new model, of this new algorithm that depends on a model, right, of how the user may act, will converge as well. And the error, up to an error that depends on the mismatch between the chosen model and the real distribution. Okay, this is okay in the sense that now we need some interaction with the user to learn the model, at least an initial model, but we don't need a constant interaction with the user, okay? Because we can run the model instead of the user, right? And then depending on how good the model is, I will give them, the thing that will come out will be better or worse, right? And despite these different algorithms, at the end, the output will be the same, right? The output will be the same. The output will be a set that I give to the user, and the user can decide whatever they want, okay? That's the output. And then the fact that I'm modeling the user with different degree of sophistication is how tight my bounds are and how tight so how much flexibility I can allow the user, in fact. Because if I know that the user will not be flexible, I can give them all the flexibility they want. They won't be choosing anything else than the decision in the middle, so then I can be very tight. Okay, very good. All right, so I would like to close, just summarizing a little bit what we have done. We have formulated some flexible optimization problems. I called them flexible in the sense that I allow flexibility in the user choices, which I think is very important looking forward. And so flexibility comes with the fact that the users now have a set of possible decisions, not just a decision that is imposed. And the algorithms are based on, they can be based on robust optimization if you like that. Okay, if you are more into trying to find sophisticated reformulations of the problem, that's what you want to do. Okay, in that particular case, you are unaware of the user. The user are almost a noise, so they can choose anything. They are not rational. Fine. If you are more into stochastic optimization, then you can allow the user to pick from a certain distribution. That's quite fancy right now in machine learning. And in both cases, we have some theory, and in the paper also a simple numerical example. Okay, but then with this, I like to close it, and if you have more questions, I'd like to take them. Yeah. Yes, please. Yeah.
Thank you so much for the nice talk.
Yeah.
I'd like to ask two questions. One of them is why don't you use zonotopes or set representation as you are using affine transformation, which is like zonotopes? I'm not sure if you are aware of this.
Okay.
Is there a reason for avoiding using that or something?
No. I mean, what do you mean exactly?
Set representations instead of intervals.
Okay.
You can use set representation that allow flexibility instead of boxes. You can have shapes.
Yeah, you can have shapes. Yeah. Just for the ease of writing down, I'm using the user to have one scalar decision and all of them to be independent. But you can have sets that are way more complicated. Yeah. Nobody. So even. So if you can model them, then you can have sets that are more complicated. You will not change the theory in the sense that you will have either you will look at robust optimization problem, right, over these complicated polytopes, or you can look at stochastic optimization for distributions over the decision they take over those polytopes. Yeah, that's fine. Yeah.
Sorry, the second question is now you have a set
Yes.
that's robust.
Right.
And then why you introduce the probability? So why don't you continue in a robust manner for the whole analysis?
Yeah, so you can do, right? So there are tools to do that. To do it's not so then the interesting part will be for a specific problem trying to find a formulation that is the tightest as possible from the robust perspective, right? However, it's limited in the fact that you model the users as completely rational. They can choose anything within this hyperbox. And instead, I would like to find tightness elsewhere, saying now instead of modeling anything between, what if, given the fact that they have the whole line or the set, they can pick things in a certain distribution. That would help me being a little bit tighter, less conservative. Yeah. So that's what I was looking for.
Thank you so much.
Yeah, no problem. Yeah.
Can you say something about the duality gap? Because it seems to me that there is a core assumption behind the lines you didn't emphasize.
Right.
But if you go back to the use of max min-max conditions, if the duality gap is not zero, given
This one, yeah.
the middle later at the end of the slides, this is a typical procedure for a saddle point to exist.
Yes.
And the duality gap needs to be zero. If
Right.
it's not zero, even the Primal dual dynamics gives you cycles.
Okay.
Is there any assumption about duality gap being zero that you?
I'm not sure. I'm not sure. I think they are under. They appear in a different way, possibly because let me see. If we have,
I think it's the assumption on strongly convex.
Yeah, I think that will is the one that will avoid to have limit cycles and other things. Right? So it's a bit under. Yeah. Right. They I think is there. Yeah. Because if you, of course, if you relax that, maybe you can have other type of behavior, but then it will be super hard to characterize this type of primal dual. You will have to go for something else, right? So this is very naive in the sense. But yeah.
So I had a question about this medial ground that you mentioned.
Yes.
And then you said, okay, you might not need constant interaction with the
Right.
users, and then somehow that would serve as a digital twin or.
Right.
But wouldn't interaction, let's say, and then you get practical convergence, but would you envision maybe another external on top of the loop, on top of what you have, that can correct for the mismatch?
Sure.
By some
Sure.
line of,
Sure.
adaptation?
Yeah. I mean, it's quite open in that sense. This is quite preliminary. The tools can be developed forward and further, and yeah. So you can imagine a system that interacts with. You can decide when to interact with the user when he observes some phenomena that he didn't predict. Right. So could be a trade-off between the exploration that it does and the exploitation of so it corrects for the mismatch. There can be many things. Dealing with users is always complicated, right? We learn from the first talk that they're very quite complex, and so I don't, so I wouldn't ask them too many questions. And yeah.
So I was thinking more from the mechanism design literature.
Yes.
So instead of like just starting the system,
right.
you have a prior step where you have asked certain questions to the
That's
users
right.
in order to approximate the distribution. Because
That's
I
right.
think the main thorn here is this unknown distribution
Right.
and
Right.
non-complexity. So it could be like, so do you have a thought? It could be direct where you like ask the question, if I give you this decision,
That's right.
what's the probability that you'll comply? Or
Right.
it could be indirect as well.
Yeah.
So have you thought about like adding this like theory from mechanism design literature?
No, I didn't thought about that specifically. I mean, you can, it's open how you estimate that distribution, right? So you could ask a couple of things. You could have like the average profile, and then you fine tune depending on the simple questions they ask. If you want to install the app, then you ask these questions, and then I take care of it. It can be done in a few different ways. It could be interesting to see. Also, you treat so it can be open to that, and it goes again in the direction a little bit of I mean, it goes in many ways, right? It goes into distributionally robust type of thing. It can go in game theory type of thing.
In this talk, we will talk about multi-agent systems. A multi-agent system is basically a system which is comprised of multiple entities that interact with each other based on common or different objectives. They're very useful for modeling the behavior of large-scale systems such as energy, social, and telecommunication networks. For example, you can use them also for V2G charging, where you have a large fleet of electric vehicles. You could model, for example, humans, or users. You can also apply it to smart grids or telecommunications. But the concepts that are of interest to me are especially two: competition and cooperation. So depending on how we consider these concepts, we have multi-agent optimization, where cooperative agents optimize a collective cost. We have non-cooperative games. In this case, you have selfish agents that they're optimizing their individual cost, but their costs can be coupled. And in the other case, you have coalitional games, where selfish agents might be allowed to form coalition if that implies that they will receive a higher payoff from the coalition that they will form. Okay, in this talk, we're going to focus on non-cooperative games, and I'm particularly interested in the challenges that pertain such systems under the effect of uncertainty. So uncertainty, as we know, can have a significant effect in such systems, and problems can be that the probability distribution of this uncertainty can be unknown, or it can have some probabilistic shifts. So in order to address this problem of uncertainty, several methodologies have been proposed. A prominent one is robust optimization, where you have solutions with respect to the worst case cost, but considering the worst case among the entire support set of the uncertainty can be often too conservative in practice. Another approach is the sample average approximation. You can use the empirical mean instead, and then you minimize, you take your decision based on the empirical mean. However, sometimes it might not be reliable out of sample. So if you have some data, and then there is some new data, this new data might not be captured very well by the sample average approximation approach. So the question is, can we find a middle ground that is not as pessimistic as robust optimization, and you have better generalization than sample average approximation, even though you have a small number of samples? And the answer is yes, there is a methodology for that. It's called distributionally robust optimization. And what it does is basically, it's like you're having uncertainty about uncertainty. So you have the data, the distribution of the data, which can have probabilistic shifts, and you consider some robustness against those probabilistic shifts. So basically what we do is we optimize the worst case expected cost over what we call an ambiguity set, a set of distributions, usually around an estimation of the probability distribution, or an estimation based on empirical data. In this work, we will focus on distributionally robust Nash equilibrium problems with heterogeneous uncertainties. Okay, so in this case, each agent minimizes their own individual cost. You have an expected value over a different probability distribution for each agent, and hi, the function that is minimized, is also an individual function. X minus I are all other agents' decisions except for agent I. And as you can see here, the uncertainty to be considered can be different per agent, which might also capture some different perception. Basically, it can be human perception of the uncertainty, or actually a different uncertainty affecting each agent. So the problem is that you might not know this probability distribution pi here. And what you want to do is to hedge the problem against the ambiguity in pi for each agent. So what you're doing is, instead of solving this problem, which you can't because you don't know pi, you take some data, ki per agent, and you consider a ball around this function. And then you're solving a minimization problem over the set of decisions, and then a worst case over this ambiguity set of the expected value. And in this work, we will focus on the Wasserstein ambiguity set and the Wasserstein radius epsilon I, as we will define later. But the important part is that the data that each agent draws can be different, and also the Wasserstein radius that each agent chooses can also be different. And this basically captures the level of risk aversion of each agent, which can actually be individual. So some agent might be more paranoid or less paranoid against uncertainty. Okay? And the main idea of the Wasserstein ambiguity set is that each agent I draws some samples. These samples have to be independent and identically distributed by assumption. And you obtain an empirical probability distribution. And then you can define the Wasserstein distance as the so-called optimal transport plan. Basically, you are trying to, you are given a transportation cost, and you are trying to minimize over the integral on the support set of this cost, such that you move mass from the probability P to probability Q through this transportation cost. And you do that over the entire support set, and you minimize in order to find a coupling, a joint probability distribution that captures, that is the solution of this minimization problem.
this has many benefits compared to different ambiguity sets, as it captures very well distance between distributions. And then you can choose a Wasserstein radius epsilon I, the same way as you do in, for example, vectors. And here you have an ambiguity set parameterized by the Wasserstein radius and the empirical distribution of each agent. And then, based on the Wasserstein distance, you can bound this quantity by the set radius epsilon I. So basically what you're doing is you're constructing a ball around the empirical distribution that you have calculated. But now the ball is not in vectors, but it is over functions. It's on a functional space. Okay, now it is important to distinguish between two things: distributionally robust games, especially heterogeneous ones, the ones that have different data per agent and different radius per agent, and distributionally robust optimization. In distributionally robust games, you have selfish agents that optimize individually. In standard DRO, you have usually one decision maker against nature. In distributionally robust games, the other thing is that each agent uses their own data, and you can have different Wasserstein radii per agent, whereas in DRO, oftentimes you have common data and common radius. And in distributionally robust games, interdependent cost functions are the essence of a game. So you have some cost functions, each agent minimizes their own cost, and these cost functions, while you're minimizing, they're interdependent. Now, this is not the case when you have a distributionally robust optimization, because you're solving just one optimization problem in this case. And there are some very interesting work. This is a seminal work in this distributionally robust optimization. Very nice, also very nice tractable reformulations. And this is a more recent work that treats, it also has some theoretic and computational aspects, and it's based mostly on regularization. Okay, now I want to be clear about the difference that heterogeneity in ambiguity sets can make. For example, consider two agents. One minimizes the first problem, and the other one minimizes the second. So you have these two uncertainties affecting the system. You don't know the probability distribution. You might also have some probabilistic shifts. So you take samples, and around this empirical distribution, you build a Wasserstein ball. Now, if these two balls were common, and this uncertainty was the same, in the homogeneous case, you would be here. However, if you have something different, yes?
Sorry, Q1, how does it appear in the expectation?
Q1 is here.
Yeah, but in the expression.
The expected value is an integral over this.
Of Xi1? So I don't see the dependency from Q1 over any of the...
Xi1 follows Q1.
Okay, so it's...
Okay, yes. So this is, yeah, sorry, maybe it's a little bit bad notation. Yeah, but what I was saying is that if you have common ambiguity sets, you might end up here, but a different ambiguity set shifts this equilibrium somewhere else. So in this case, this heterogeneity leads to information asymmetry, or information asymmetry in the case of data, and if you choose different Wasserstein radii, you have something like risk aversion differences. And in this case, you have a different distribution robustness equilibrium to which you converge. Okay, now there is a clear relation in the literature about the connection between stochastic games and variational inequalities. For example, consider the previous stochastic game that we had. We minimize the expected value over pi, and then you can write the problem as, under some conditions, you can write the problem as a variational inequality problem, where f of x is the so-called pseudo-gradient mapping, where you take the gradient with respect to each of the costs of the agents. And then in this case, a stochastic Nash equilibrium is a point x star, where it's like the choice of no regrets. So no player can decrease their expected cost by unilaterally deviating from this strategy here. So given x minus I, and you have here the expected value over pi, I have done my best as player I to satisfy my cost. So as I said, under convexity of hi, and these are the conditions actually, under the convexity of hi and also convexity and closeness of xi, you have this equivalence. So this is the take-home message for the relation between stochastic games and variational inequalities. Now for distributionally robust games, something similar holds. Each agent solves this min-max problem. Then you have pi as the empirical distribution of each agent's data, and you construct the Wasserstein ambiguity set based on that. Then the distributionally robust Nash equilibrium problem is defined in a similar way, given x minus I, but over the worst case probability distribution that can happen here. So it is the choice of no regrets, but in the worst case scenario over the ambiguity set. So in this case, you have the following result, that you can consider the distributionally robust variational inequality problem of this form, where the mapping is the pseudo-graded mapping again, but here Qi star, the difference is that it is the worst case probability distribution at x star. Okay? And then you can show that the distributionally robust solution set is actually equivalent, if you don't have coupling constraints, to the solution set of the distributionally robust variational inequality problem. Okay, based on that, you can actually derive some interesting properties about the problem. So you know from the literature there are results in out-of-sample guarantees and that also rely on other inequalities, concentration inequalities. And if you take the individual Wasserstein balls of each agent, you can say that with confidence 1 minus beta I, the probability, given the data that you have taken, that the true probability distribution lies within the Wasserstein ball that you considered, is bounded by some, the probability, yeah, so it's a probability that it relies, so you have that with, with very high confidence, the true probability is within the ambiguity set. Then, if you want to provide, however, confidence certificates for the out-of-sample robustness of the Nash equilibria, you cannot actually go individually. You have to have some kind of collective bounds. So in this case, you can show the following result, that with high confidence 1 minus sigma I beta I, so if usually beta I is very small, so it's like 10 to the minus 10 or 10 to the minus 9. So if the agents are 10, instead of 10 to the minus 9, here it would be 10 to the minus 8. But if they are more, it could be a little bit worse. But with this confidence, any distributionally robust Nash equilibrium xk star would satisfy this condition here. Which means that the distributionally robust Nash equilibrium is also robust against the true but unknown stochastic Nash equilibrium. Now, another result that you can obtain based on some derivations is that you can have a bound on the distance between the distributionally robust Nash equilibrium set and the equilibria of the original stochastic Nash equilibrium set. And then you can leverage this bound in order to show asymptotic consistency properties. This means, asymptotic consistency basically means that as you increase the number of samples and as you decrease the Wasserstein ball, you know that this distributionally robust Nash equilibrium will converge to the true equilibrium for certain conditions on the confidence parameters. And this is also, these properties are proved in this paper here. But before proceeding, it is important to define basically what has been defined already. I think Andrea defined strong monotonicity, where these conditions should hold, where you have a quadratic. But in case the mapping is monotone, you only require this condition to hold. So monotonicity in variational inequalities is like convexity in optimization. Okay, now the question is, how can you compute such equilibria? So one approach, basically 80% I think of the literature in DRO uses epigraphic reformulations. So one approach could be to leverage the dual problem and perform an epigraphic reformulation. And then you have that an infinite dimensional game can be recasted as a finite dimensional generalized Nash game. And then you can use different algorithms, for example, the golden ratio algorithm, in order to calculate the equilibrium. However, depending on the structure of the problem, solving with an epigraphic reformulation might be more or less challenging. For example, we can consider now this polytopic set. This is the support set, so the uncertainty takes values inside the polytop, and then each cost function can be written as a point-wise maximum, where these are affine functions with respect to psi I. Then, under certain assumptions, you can show that the distribution robustness equilibrium of the original problem can be written in this form. Okay? However, sometimes x minus I can create issues. And I will show you an example where it doesn't create issues and an example where it does create issues. Consider the following heterogeneous risk-averse peer-to-peer electricity market, where you have generation bounds, bounds also on demand, so you have different market participants trying to minimize their own cost, and peer-to-peer trades as well. So you are allowed also to sell energy over the network to someone else. And then you have some trade limits. You cannot sell too much energy. You have some reciprocity. What you give to someone is the same as what someone receives. And some power balance constraints. And then you have for each market participant the generation cost and the P2P trade and the demand cost. Okay? In this case, the results are very good from convergence perspective. You have 5 market participants in this case. They can be prosumers or generation firms, and you have to solve this problem, this min-max problem, subject to the constraints that we talked about. And each market participant can again use any Wasserstein ball they like based on the data and the radius that they choose. In this case, they choose in between here, a radius in between this. Okay, but in this case, there is no actual dependence of the other agent's decisions here. There is only uncertainty affecting this cost. And then there is only coupling in the constraints. So the other agents only affect the problem in the constraints, even though you're solving an individual, each agent solves an individual cost function. In other problems where you actually have this interdependence and then you do this epigraphic reformulation, what you will observe is that this epigraphic reformulation usually converges, but this is empirical. You cannot have guarantees for this algorithm as of now. But they introduce many, many oscillations. This is logarithmic. It looks better if it is non-logarithmic, but logarithmic captures the information way better. And as you see, there are many oscillations before converging. However, another thing, and I can also provide some intuition about that. The intuition that you see oscillations is that in DRO, you do an epigraphic reformulation. It's one single problem, you can solve it. If you do an epigraphic reformulation in games, you had a cost here that used to depend on the other agents. Now this cost has moved here. So you have x minus I and x minus I, the other agent's decisions. But because this is part of your cost, you do not share it. It's coupling because they actually affect you, but you do not share it, otherwise you change the problem. It's like you reveal some part of your cost function. So if you don't introduce any coordination scheme for that, which would imply that you change the problem, you will you will naturally see oscillations in this case. And here you see the result from different equilibrium points that have been acquired for this. So here we increase the number of samples, and as we see here, the costs of each agent, in the cost of each agent, you have a variance decrease. And another thing that we did is we increased the Wasserstein radius, and as we expected, the J1, J2, and J3 increase because they are more robust, because you consider a larger ambiguity set for the inner max. Okay, and yes?
Do you know exactly when the oscillations occur, or is it an open problem?
When oscillations occur, like
Yeah,
an event triggering.
No.
Okay.
So in your approach 1, you have to solve this particular
You know,
oscillation problem.
you know when oscillations occur.
Yeah.
They occur because this guy is not. So you have. These are not like coupling, like set coupling constraints in this case. They're coming from an epigraphic reformulation. So you haven't set them with the others. They're yours. You minimize with respect to them, but they are affected by x minus I. So x minus I is like a perturbation that's coming to your system. And after a while, these perturbations go away, but with increasing number of oscillations, but smaller oscillations, and then you converge. So I would say that for certain systems, it is always there as long as this affects you. This is my answer. And I think this is also a limit algorithmically, like because this introduces a problem class that you cannot solve using the available methods in distributionally robust games, for example, because all of these games assume shared constraints. In this case, if you do shared constraints, if you share that with them, you change the problem. And then you solve another problem. It's monotone, it's nice, but it's another problem. Yeah. Okay, so another direction that one could take is find some structure and directly compute the inner supremum. Then you can reformulate the problem through Kantorovich duality. We will see what this means. And then instead of a distributionally robust game, you usually end up with a robust game. So this inf sup, you make it something like inf, which is like standard minimization problem. Minimization in the sense that each agent minimizes their own cost. Okay, so in this case, an interesting problem is to consider a 2 Wasserstein distributionally robust game where you do min-max over the ambiguity set of each agent. Fi is convex in xi. Gi has this quadratic form with respect to the individual uncertainty, and it has also this term that couples uncertainty and an affine term of the decisions. And we assume that it is written in this form. Qi can be written as Li transpose di Li, with Li being orthogonal and di a diagonal positive semi-definite. Okay? So in this case, Kantorovich duality looks like this. Instead of having this infinite dimensional ball, again you have a supremum on the support set here, and you have to, it's like you have a sum of supremums. So you have the decision that you had before, the agent's decisions xi, but you now have another variable, lambda I, that you need to find in order to solve this problem. Okay, this looks as a significant simplification of the problem, and you can show that actually robust equilibria of this problem correspond to distributionally robust mass equilibria of the original one. The other way, it's not certain. You can show it one way, and maybe for the other way you can show that there exists a lambda that corresponds to some other variable for the inner max. But for now, this is one way. And I think in general you cannot show it. Yes? Okay. And this is in this result, also the previous structure of the problem is in this paper that we have with Reza and Sergio. But you can actually go a step further. So you have here the inner soup. You can actually go and calculate it because you can leverage the structure of this problem. And then the resulting problem, instead of having lambda I greater than or equal to 0, you will have lambda I being constrained on the maximum eigenvalue of Qi. And the rest of the problem has this structure that we see here. Okay, now this looks like, okay, we have taken care of the min-max. We can formulate it as a VI, as a standard VI. Okay, you can also, these transformations complicate a little bit, but they don't change much. Okay, but the problem is the following. You have this game. You consider a variational inequality problem, and you calculate the pseudogradient. If the pseudogradient is monotone, everything is fine. And in distributionally robust optimization, if you consider just one agent, and there is no coupling because it's just one agent, it's also monotone, so you can solve it quite easily. In this case, we cannot show that it is monotone, and also experimental evidence shows that it is not all the time. So the interactions between the agents and the different ambiguity sets can result in non-monotonicity. However, one can use really nice algorithms in order to calculate this even in non-monotone VIs. So one algorithm that is also part of another presentation in the following days at ECC by Nicola, Reza, and the rest of the team, is basically a hybrid version, a mix of two algorithms. So you have standard projected gradient descent, where, okay, it requires strong monotonicity, theoretically, and knowledge of the Lipschitz constant, but then you have to tune the step size. But then you can also have a golden ratio method. The golden ratio method adds a momentum term, and then theoretically what it requires Lipschitz continuity, but you don't have to know the Lipschitz constant, and it requires also monotonicity. And it works for monotonicity. What we're looking for is a little bit different. It's like, because this algorithm introduces a momentum term, you know that it will converge in cases where this will not converge, but it can be slow sometimes. So what we're doing is we're using some terms in order to identify when oscillations begin. For example, you use the fast algorithm, you identify when oscillations start to happen, so you know that you will not converge. And in this case, you switch directly to the other method. And then you save a lot of time because of the switching, because you use the fast algorithm when you know that you want to get close to the region, and then to get exactly to the region, you use the other algorithm. Okay, so the take-home message is that phi k is, in this case, updated adaptively using this switching between the two algorithms. And this excessive negative momentum is reduced, which enables us to have a little bit more aggressive steps. And as I said, even though it is designed for monotone mappings in theory, it can actually converge also in the case of non-monotone mappings. So here are some statistics, and this is also for different sample sizes. So we can see that more or less the iterations are the same. However, the computational time might be a little bit different. So each iteration takes some time. In this case, the computational time might be a bit different. But the convergence, as you see, in the forward-backward case, which is like a projected gradient descent, is this. In the case of golden ratio, you have the blue one. And in our case, we have this hybrid algorithm. Even though it works better in practice, you cannot show that it works better than this algorithm in the worst case. So there might be instances where they coincide, but in practice you see improvements because of the philosophy that I mentioned. Okay, and a final thing that I want to mention is a little bit preliminary. We're looking to model a vehicle intersection but it's a simplified version. So you have an intersection and you have certain paths that have already predefined for the vehicles. So each vehicle go, if they want to turn right, if they are in the south road and they want to turn right, there is a predefined path from 0 to 1 for them. And then you have to choose a constant speed to go from this 0 to 1, which is predefined. But what we want to do is, in the cost, to introduce some risk-averse collision avoidance term along with reference speed tracking. And under certain conditions, you can show that a monotone mapping can be obtained. This is usually when this term is a little bit more important than this term. Otherwise, you might have non-monotone cases. For example, here we might consider two vehicles, vehicle A and vehicle B, and they want to track the reference signal and at the same time don't be too close together, while this theta parameter shows the risk aversion during the intersection. So you can actually model that using distributionally robust approaches, and then you consider a Wasserstein ball around the probability distribution of each of those parameters, and you solve the problem. And this is subject to very simple dynamics, so you just have a scalar that follows like the definition of speed. And I don't know if I can play the video. No, I cannot play the video, but I have it. Sorry. Can you see this? Okay. Let me find it. Okay, so in this case, what we have is we have considered that the risk aversion, there's no risk aversion, the Wasserstein-Reddy are 0. And in this case, they can also be considered different per vehicle. So this vehicle wants to go that way, this vehicle goes straight, and this other vehicle wants to turn that way. And then we consider the same with Wasserstein ball of 0.1 for the second term. And what you can see in this case is that in the second case, vehicle, I can even show it again once more. Vehicle 1, the vehicle in red, is more aggressive when you have a higher ambiguity set, and these two are less aggressive. So in this case, it is not that all of them are risk averse, so they stop, but actually this vehicle tries to minimize, to maximize the distance with the other vehicles, so it becomes more aggressive towards the intersection, while the others start to decelerate. Let me show it again to you. But of course, this is a simplified example, and in order to make it more realistic, there is much more to be done. Okay, let me go back to the... Okay, so this brings me to the conclusion. What we have done in this work, we established, we considered data-driven distributionally robustness equilibrium problems, and we established a connection with variational inequalities. Based on that, we provided some out-of-sample guarantees, and then we derived the bound on the distance between solution sets of distributionally robust problems and stochasticness equilibrium solution sets. Then you can show interesting properties that are in the literature of DRO, but not for games, such as asymptotic consistency of solution sets for distributionally robustness equilibrium problems. And then you provide the means to calculate such equilibria in some challenging cases. Now, there is more work to be done towards many directions, I would say. One, you can extend games such that you have ambiguity both in the cost functions and the constraints. And another thing is you can extend the framework for nonlinear risk measures. Imagine that you have min-max of another measure instead of expected value. You could have variance, for example, or a different measure. Another thing, if you want to obtain a different kind of reformulation is to see how you could extend results that have to do with regularization in distributionally robust optimization. Many times in distributionally robust optimization, you can obtain some reformulation or some upper bound that looks like a regularized empirical mean. In this case, can you do something similar for games? This is the main question. So that is all. Thank you very much for your attention. And any questions, you can send me an email. And also ask me.
So maybe this is a fourth point for future work.
Yes.
There is an emerging literature at the intersection between federated learning and collisional games.
Can you define federated learning?
Federated learning and collisional games. And the idea is players share data.
Okay.
And you want to assess the value of sharing data. In your setup, every player has a different distribution.
Yes.
Is there any value if the players share data and they converge to the same probability distribution? So in your setup, is there a value to accommodate this aspect?
No, because this involves interaction and data sharing. Yeah, it is for future work, this one.
But if the player have the same distribution,
Yes.
how does it reflect in terms of property of your national league?
If the player has a different or the same?
If the player have the same distribution.
If the problem has the same distribution, again, it's not distribution robust optimization. It is a game with the same distribution, and whatever you see here, it's usually monotone. So you can calculate it.
You shrink the uncertainty, the ambiguity.
You can also do that. You can collect more data and also make the Wasserstein radius adaptive to that and start shrinking the ambiguity set in order to converge to one.
And that creates a value, right?
Yes.
So that's the value from collisional games. So if two people share data, you reduce ambiguity and you create added value.
True, but I was thinking. Yeah, but this has to do with the fairness of value in coalitional games, right? Or is it a way to quantify the value? It's a way to quantify the value?
The second, it's a way to quantify. So what's the
Okay.
value of aggregating data?
Okay.
So all the players in a coalition, they share data and they get consensus on the distribution.
Yes.
That must have a value. And
Yes.
we want to value, to assess
You can do that if you cleverly adapt the Wasserstein radius based on the data that you have. Yes, you are able to do this. This is my thought on that. In coalitional games, what I have studied is stability of coalitions. So you consider different ambiguity sets per coalition, but this is restrictive because it does not include sharing the data.
Yeah, that's the one.
So yeah, I think this is very interesting, and I was thinking of it.
Because we always talk about sharing resources, but what if we share data?
Yeah, I completely agree with that.
They also have a value.
Yes. And this has to do also with the fairness part, I think, and also with the stability of allocations. Okay. Thanks for the question.
I'm gonna start talking about transportation networks, more in particular, which is one of those cases where the interactions between cyber layer, the physics of the system, and the human decision maker is the most evident. I think it was mentioned already in the previous talks, but I guess mine and the following talk will be most focused on the transportation application. Now, we all know that transportation networks are often inefficient, and partly this is due to the fact that the users set up on equilibria which are not optimal or are far from being optimal in many situations. And I will aim and look at two different mechanisms that should improve the efficiency of the system in transportation networks. One is dynamic pricing, and in particular I want to focus on what kind of information would be needed to implement a dynamic pricing mechanism. And the second point will have to do with uncertainty and how uncertainty on the system can be leveraged potentially by system planner to reduce the inefficiency, how to design private signal policies in All right, so I'll probably mostly focus on the second problem, and before jumping even on the first one, I will just make a very brief recap of something that is super classical, but in traffic, but perhaps not everyone knows outside traffic networks, which is traffic assignment problems. And imagine that the network, and I'm going to talk about single origin and destination for the whole talk, just for simplicity. There is a network, there are links, you can think of them as a chunk of roads. Nodes are intersections, there is one origin, one destination, everyone wants to go from the same origin and destination, and every link is endowed with a delay function which tells you what's the travel time on that link as a function of the flow on that link. Now, the fact that this is increasing, it's the congestion effect. The more vehicles are on the link, the more it goes up. And if you look from an optimization point of view, then what a reasonable measure of performance would be, it's the total travel time, which is the sum across all the links of the flow on that link times the travel time on that link. And this ends up being a convex problem, to optimize overall possible flows. And it's nice from that perspective. However, and this is the classical setting where you think that drivers choose their own route, then you typically end up in a different setting, and there is this notion of user equilibrium, which it's sort of a Nash equilibrium for a game with a continuum of players in this setting. Was introduced by Wardrop in the 50s, and it says that you are at equilibrium when the journey times on all used routes is equal, and it's less than or equal to the journey times on any unused route. Now, you can translate that into math. It becomes a set of variational inequalities that were already mentioned before, but it's also, you can relate it to a different optimization problem, again, a convex optimization problem. It's the same, you are minimizing over the set of flows, again like before, but just what changes, it's the objective function. So the users, by equilibrating and trying to look at their own travel time instead of a global objective, they end up minimizing something. This something is just not what the system planner would like to, but it's something different, which is the sum of the primitives of these delay functions. When there is no congestion, the two problems coincide. So when these functions are constant, the two problems coincide. But otherwise, in general, they differ, and there's a huge literature studying how different the system optimum can be from the user equilibrium, can be from the system optimum, how inefficient it is. There's this notion of price of anarchy. And there's also a classical result which goes in the direction of the mechanism that we want to discuss, which is more than 100 years old result, which says that there is one idea, which is from economics, which is marginal cost tolls. If you introduce tolls with a certain structure, and we will discuss why the structure, in this case they're equal to the flow at the system optimum times the derivative of the delay function in the system optimum, then you are, economists would say, able to make users internalize their negative externality. In the sense you align the equilibrium with the system optimum. Now, what's wrong with this solution? It's that it's a static notion, it's a centralized notion. You have to compute the system optimum, compute the tolls, implement them, and if something changes, then you need to restart and change completely the setting, so they are not adaptive. And they don't take into account several factors. In particular, I will talk about uncertainty in the second part of the talk. But there are also many other assumptions. One of them is homogeneity of the preferences of the drivers that I'm not talking about today, but it's a very interesting issue. Now, first theme, I want to talk about traffic dynamics and distributed pricing mechanism, and I want to present a multi-scale model for traffic dynamics, where I propose an implementation of distributed pricing. And behind the formulas that I'm going to show, there is this idea. There are two layers at this level that you should imagine. There is the physics, as we said. So this physics is going to be a conservation of mass. There's a flow of vehicles moving around the network. So there's going to be a density and the flow, and the derivative of the density is going to be dictated by inflow minus outflow. And then there is a decision level. Drivers choose which route they are taking. Again, imagine for simplicity, we're focusing on single origin, single destination. They have several paths to go from the origin to the destination. They choose their path, but of course they can revise their choice because they get informed by Google Maps or Waze or the app that something is changing in the network, and they might adapt to these changes. Perhaps something that is not completely real time, but with some frequency, they adapt their choices. Now, there are going to be two layers, two time scales, one for the physics and one for the decision layer, let's say. Let's look at the physics first. And here are some of the variables that I'm going to use. Imagine that on every link, there is a variable xi, which is the density, the normalized amount of vehicles on that link. Y is the outflow, and this outflow is related to the density by a function which is again nonlinear, and it's sort of a saturation like this. Again, the nonlinearity is important. Where this function linear, there will be no congestion effect. The congestion is in this function, and you can dimensionally find out what would be the travel time. At least when you know, if you look at density divided by flow, then this is time, and this time you can go back to the function that we had earlier, which would be the travel time as a function of the flow on that link, which is the same shape as before. Now, how does the dynamics evolve at the physical level? We have again the density. The density on the link I changes in time. And it's a conservation of mass. It's inflow minus outflow. What the outflow is, it's yi of t. And what the inflow is, if you are at the origin, you have inflow from outside the network, vehicles that are entering. But you also have inflow, if you are an intermediate link, you have inflow from coming from links that are pointing towards you. And what this Rji is, that's the fraction of vehicles that coming from J turn to I. Of course, it's something that is non-zero only in contiguous links, but it captures the driver's decisions, right? They decide where to turn at each junction. Now, I'm going to couple this R of t with the path preferences. Okay, and this is going to couple the two layers. So the second layer is going to be something which is related to the decisions of the drivers. And again, we are thinking of the simplified setting with one origin, one destination. So assume that there is a certain quantity of drivers that choose a certain route. There are several routes from the origin to the destination, finite number of them. When you want to go from O to D, you choose one of these routes. The number of drivers, the mass of drivers choosing this route gamma, I'm going to call it Z gamma. And how do I relate the routing matrix to this path preferences? The fraction of people turning from I to J, I will relate it in this way. This is the, what I take is that I project this path preferences into the links. This AZ would be a projection onto the links, and then I normalize and I take the turning rates exactly from here. Now, this explains how the decisions affect the physics level. But now there's a second feedback, which is once the decisions change themselves, and they change in response to the current congestion levels on the different links. Okay, so I'm going to introduce a dynamics for Z. Z is going to be changing in time. And I'm considering this dynamics, which is, it goes under many names. Logit response is one, quantal response is another one, noisy-based response is a third one, and so on and so forth. Essentially, what I'm going to say is that I'm going to assume that, and I will discuss then, this will be my control variable. This will be a toll on link I. I'm going to call it wi of t. I'm going to change it in time. And I'm going to say that the perceived cost by a user to use link I is going to be the travel time plus the toll. Of course, I'm assuming here some normalization that I can sum time and money. And then the path preference updates, it will be this function. So there is a parameter eta, it's just something that measures the frequency of these updates. And then there is this f beta, which is a logit function, which says that beta is the inverse of noise. When the noise vanishes, beta goes to infinity. It means everyone is going to change the path with the minimal travel time, according to the current information. With beta, which is finite, I'm going to allow for some limited rationality, if you wish, and with certain very low frequency, people will choose also inefficient paths. Okay? And this has this effect. Also, of course, it makes the system smooth, which is much easier to be studied. All right, now the idea is the following. You end up with two layers. So there is the decision layer, which we discussed, and there is the physical layer, which is this, and they are coupled by the decision Z that comes from the decision layer. They affect the physics of the system. And let me emphasize, you have the travel times, those that you read on Google Maps here, but also you have this dynamic pricing that I'm introducing, which is something that we want to design in order to get the most efficiency. Now, the result that we have, and I'm going to be a bit fast, is that, let me show them all points together. If you have no tolls, and this is sort of what you expect, then you would converge globally around the user equilibrium, the one that could be inefficient depending on the structure of the system. In general, you could think that you're using pricing policies that have to be monotone. Decentralized means that the cost on link I depends only on the flow on that link. Okay, so it's completely decoupled from the others. And monotone means that it's monotone, non-decreasing in that quantity. And this result generalizes, so you still get global stability around something which we are going to call it an induced user equilibrium. What is this induced user equilibrium? It's something that changes and that you can shape depending on your choice of this feedback. And if you choose the marginal costs, okay, the good ones, but used in feedback, not in a static way, but using that, then what you get is that you can globally stabilize the multiscale around the social optimum. Now, why is this good, and why is this particularly efficient? Because this feedback marginal costs, they don't use any global information. So they adapt to changes in the network automatically. They don't even need to know that there is a network around them. All they need to know is the form of the derivative of this delay function, which is local information. Please.
The existence of user equilibrium and social effect is guaranteed under this?
I'm working with differentiable increasing convex functions. But under those assumptions, it's always ensured. And when I add this with this property, I keep the properties also induce equilibrium. Yes?
Can we think about this derivative as like a d term?
Which term?
That tau prime?
Yeah.
Do we really need to know the function, or can it be implemented just as a derivative?
It can be implemented as a derivative, yes.
Like
yes.
like a d term?
Yes, I can.
Just from measurements?
I can just measure it, yes, I can, yes. It's just the derivative, and I can try to estimate it as much as I want. Yeah, so the strength, I think, here is that is the information structure. There is no need for global information, and once again you achieve a global objective with something which is completely local. In that sense, it's also resilient. If something happens to the network, you will move to the new equilibrium and to the new social optimum without having to reconfigure the system. The system reconfigures itself through this. Now, let me emphasize technical details. Okay, we can prove it for small eta. Eta is the frequency of updates. Okay, that means that you look at Google Maps not too often. Okay, but that's more of a technicality, it appears, because if you do extensive simulations, you see that global convergence doesn't depend on eta. You can also notice something that from numerical simulations, that this feedback marginal cost outperforms static tolls not only in the asymptotic behavior, but also in the transient, which is something we didn't prove, but it seems to be evident. And something we looked again numerically, it's how robust these things are with respect to delays in the update. So I'm assuming this, you get information, instantaneous information, but let's say this information is 1 minute late or 2 minutes late or so on. So what happens in the system, and you see that with feedback marginal cost, you are slightly less robust with that. So you can handle delays until a certain threshold, and all of a sudden, then you end up in oscillations, as you might guess. Well, very often in control, when you add the feedback loop with delay, you can end up in that. We have no theory for that, but that's an observation. All right, so let me get to the second set of model that I want to discuss, and here I'm going to move back to a static setting. The new thing is going to be that there's going to be uncertainty about the travel time. So again, we have a transportation network. It's a directed multigraph. We have a single OD pair. Let's say the throughput, so the total mass of vehicles from the origin to the destination, let's say it's up to 1, just to simplify the exposition. And again, now I'm calling the flow on the link, I'm calling it F. Sorry, I changed the notation, but Z is still the flow on a path. And here is the new part. There is a random network state. Okay, theta is going to be a random variable, taking values in some space, and there is an a priori distribution of this theta. And why do we care about this network state? Because the travel time on a link E is going to depend on the flow on that link and on the network state. Okay. And again, it's going to be increasing and convex in FE. To go back, those are the assumptions that make sure that we always have one equilibrium. Now, what should be the, from a system optimization perspective, what should be the new cost? We had the total travel time. We can say in this case, the expected total travel time is now the most natural system objective. And what is it? It looks more complicated, but it's similar to before. Summing over all links, the product of the flow on that link times the delay in that link, except that they are now random variables because they depend on this random state. And then I'm integrating against the prior distribution, so I'm taking the expected value of this travel time. Just observe that the flow, in general, can depend on the network state. So if I have full information for every state, one way to think of it is for every state, I choose what's the best flow, and then I optimize that. Yes?
So in the transportation network, in those routing games, what would state represent here?
State could be one road that is closed, or one lane of one road that is closed, or something that is slowing down, and you know that
some construction going on. That
it's a construction, yeah, maybe the construction you know about it, but something a bit more random, that you have some a priori distribution, or you know that that area, I don't know, very often around that time it gets clogged because of some activity that goes down there, and so on. Think of something like that's a good question. Think of something like All right, so the system optimum is the one that maximizes this, and it minimizes this, which is very similar. Another question is, what information should we give to the users if we are the system planner? Okay, we can, of course, we could say, let's give full information. Everyone is the best app possible, gets instantaneous information. This is static, so it's full information, everyone is fully informed. Then, if everyone is fully informed, then you get a user equilibrium, which is, okay, state by state, it's the same equilibrium as before. Okay, so this is the total travel time on a link on a path I is less than or equal to the total travel time on a path J. If someone is choosing path I, then that should be true. That's wardrobe, theta by theta. On the other end of the spectrum, there is no information. Nobody knows anything except that they know their priori distribution. This is Bayesian setting. Everyone has the same prior. Let me emphasize that. Then what would be the user equilibrium? Then every path that is used, if it's used, then the expected total travel time of that path should be less than or equal to the expected total travel time on any other path. Okay, now, both of them are inefficient. And you can see it on a very simple example that I borrowed from the literature. Okay, so let's say that you have a network state which is 0 or 1 with probability 1/2. And let's say something very simple. You have two links. One link which with probability 1/2 has travel time 0. Okay, it's an extreme example, of course. And with probability 1/2, it's 1. Now, of course, we all agree is that if the theta is 0, then we all want to take this path. The cost is 0, it cannot be better than that. And if the theta is 1, then we have two different solutions if we look at the system optimum or at the user equilibrium. Okay, in particular, if we look at the system optimum, then we get that the cost is 17/36. That's just the numbers that you get. And if you look at equilibrium with full information, then the cost is 1/2, which is slightly more than that, 1/8. Okay. And if you have no information, you also get 1/2, which is still suboptimal. Okay, so you can play with these examples. And indeed, you can show that very often you can also have full information. The user equilibrium with full information can even be strictly worse than the user equilibrium with no information. It doesn't happen with parallel links, but if you complicate the
two questions.
Yeah.
What does full information mean? Like the agents have know the realization of data, or
full information? Yes, means users know the realization of theta, observe theta, and take decisions. No information means users know the prior distribution, and then they take decisions without knowing theta, but only its distribution, so they minimize their expected travel time. Okay, we could. So what is the goal? It's, let's say you can decide how much information you give. Those are the two extremes. Everyone has full information, everyone has no information. Again, no information for me, it means the prior is known. Okay, I'm fully Bayesian, so the prior is always known. And then you have two sets of policies that you can think of. One is public information. I will give some information, but that's the same information to everyone. I will not discuss it. It's a special case if you want of the next one. I will not discuss it because you can prove it's inefficient. Again, you can make examples where it's inefficient. What is a private information? Private information, it means that we have a continuum of users. Let's say it's the interval 0, 1. X is a user. He lives in the interval 0, 1. And then I'm the system planner, and observing theta, I will decide what signal to send to every player. Okay? So it's a map that maps state and this continuum of users into a signal. Okay, now, this set of signals, where the signal takes place, can be arbitrary, but then you can prove that something is sufficient. The set of signals that it's sufficient, it's the set of paths. Okay, there is something called the revelation principle by Bellevue and Morris. You can extend it to this setting where you have continuum players, you get exactly the same. Okay, there is some related work and that I mentioned. Now, you look at this private signal. So you have this S of theta x. Okay, one thing that, that is particularly useful is knowing what is the fraction of users x that receive a certain signal k. Okay, that's going to depend on theta. For every theta, you measure how many people you have given recommendation k. That's going to be important. It's sort of going to be a sufficient statistics to evaluate this system. So if you have a signal policy, then you identify pi k, but you also can go back. How can you go back? If you have a pi k, you can always find a policy which is in this way. Okay, now I go a little bit. So if you want on a given theta, to assign a certain fraction to every, of course there are several ways you can do that, but there is one that is the most fair, you could say. And how can I do that? I know that I want to give 1/3 and 2/3, 1/2, 1/4, and 1/4. Okay, I will, and I say, and I divide the interval into these three chunks, and then I will take x plus a uniform random variable in the interval 0, 1, modulo 1, and then I will assign to x this. In this way, I'm randomizing the signal that I send, but I make it more fair. Otherwise, I make it completely fair. The probability that someone gets that signal given that state, it's going to be the same. Okay? So this formula means exactly that. Okay, the randomization that I do, it should be independent from theta to make everything sense. Okay, now if I do that, then pi k of theta, that becomes the conditional probability that the user x receives signal k given theta. It doesn't depend on x. Okay, in that sense, it's fair, and not everyone has the same probability of getting that signal. And it's a one-line exercise that the posterior distribution for those who receive signal k, it's this one. It's pi k divided by the integral, pi k integrated. All right, that's useful because now I can define what a Bayesian equilibrium associated to a signal policy this type pi is, and it's sort of wardrobe principle based on the posterior. Okay, so if you think of that, I want a flow that is the projection through the matrix P, A of my policy, and if you read here, this left-hand expression, that's expected, conditional expected travel time on J for users that are recommended I. And this is the expected travel time, the conditional expected travel time on K for users that are recommended I. Again. Okay. So this formula says there is this matrix P, so it's a bit more complicated. If I'm recommended I, Pij, think of it as the fraction of those that are recommended I but choose J. When is it that if I'm recommended I will choose J? I will choose J if J seems to be the best, according to my posterior distribution having received I, of all the paths. Seems to be the best means the conditional expected value is the minimized in J. Okay, that's the formula, what it says. Okay, it's if you think of it, it's sort of the natural extension of what. Now, here is the first proposition, which goes in the existence and then uniqueness. So I can, if you, there is this nice generalization of the result I was showing in the beginning that was saying that wardrobe was the minimizer of some function. And here too, wardrobe is the minimizer of some function, and this function, it's a bit more elaborate. Of course, there is an expectation with respect to the prior, but see, you can recognize there is this primitive of the delay function taken in some way, and in this way. Okay, so the you can prove a proposition. We prove a proposition, and that given a signal policy, the flow is a Bayesian equilibrium if and only if it's a minimizer of this function. Okay, so in terms of game theory, you could say that this game that I'm not defining with a continuum of players, it's a weighted potential game. Okay, and that's all right. Now let me speed up a bit. Okay, so what is the cost associated to the policy? Now that you are saying, so this is saying that basically if you have a signal policy, then you have a unique user equilibrium. Then you can set up your problem as the cost associated to your policy is the cost associated to the unique user equilibrium associated to that policy, okay? And so the idea would be the optimal policy problem, you want to minimize the cost over all policies of the induced equilibrium. And there is a second part of the revelation principle here, which says another thing. The first part was saying it's efficient to use the set of paths as the set of messages. The second part says something more subtle, but is the following. It says that, remember that matrix P, Pij was the fraction of those that were chosen I, were told I, and they were chosen J. You can get rid of that if, in the following sense, for every policy phi, there exists another policy, phi bar, which has the same cost, and where that matrix P is the identity. And for that matrix P to be the identity, that means that, again, this inequality, whenever you're told I should be the best for you with respect to all the alternatives. Okay. So the conditional expected travel time on path I, given that you receive I, is less than or equal to the conditional expected travel time on J for every alternative J. On J, given that you receive I. Okay. All right, so with this revelation principle, you can rephrase the problem, you can formulate the problem, and you have a single level optimization. Now, instead of having a multi-level optimization, because here you had an optimization, but then to find f pi, that was the result of another level optimization. With this trick of the revelation principle, you end up with a new optimization, which is single level. You have an objective function, and then you have a certain bunch of constraints, which are those, they're called obedience constraints. I would have called them convenience constraints, but it was already set up. Okay? Those are the constraints that if you receive I should look the best for you. Now, why is this problem difficult? This problem is difficult not because of the cost function, which is convex. It's difficult because of the constraints that are typically non-convex. And they're convex in very special cases, but we can discuss that. Now, what is the price of anarchy? The price of anarchy is the ratio between the cost that you have in your optimal policy against the cost that you have in the user optimum. And what we did, you can go in different directions, and now I'm specifying the direction that we took, is we looked for conditions under which we can guarantee that the price of anarchy is 1. When is it that this happens? This happens if the system optimum satisfies the obedient constraints. So when is it that the system optimum satisfies the obedient constraints? Let me go back to the example. Right now, the system optimum here was to send everyone on link 1 when this link has 0 travel time, and to send 5/6 and 1/6 in case when theta is equal to 1. Now, let's say your signal policy is you tell everyone to go on the first link in case theta was equal to 0, and you tell 5/6 of the people to go there and 1/6 to go here in the other case with that randomization that I was telling you. Now, would that be, would people follow the obedient constraints? And you can do the math, and you can say that, you can check that the obedience constraints are satisfied in this case. So if I implement this policy, I can achieve the system optimum in this way, in this set. Now, question is, when can you achieve it on a broader set of setting? And let me go from the simplest to the more complicated. If you have 2 links with a fine delay function, a fine delay functions would be something like this. where there is uncertainty for simplicity. I put uncertainty only on the constant term, but not on AE. Okay, you can do the math here. The problem reduces to this, and you can compute what the full info system optimum is. And then you have a first theorem, which is an if and only if. You have price of anarchy 1, which means the system optimum satisfies the obedient constraints, if then only if this inequality is satisfied. Okay, the first, it's a convenient assumption on the support of delta. Delta is the difference. Everything depends on the difference between B1 and B2. In this case, you can get rid of one random variable. And what is this saying? This is saying that the second moment should be greater than the first moment. You can rewrite it as saying that the variance is sufficiently big with respect to the expected value. That's intuitive, because if you have no variance, then it's a deterministic problem, and then you know that it's inefficient. Okay, so you need some variance to induce the desired behavior. Okay, you can put here, it's a plot of how much variance or how much standard deviation you need as a function of the expected value of this function delta, and you see this sort of plot. Okay, then we have other results on this special case. Here you can compute everything, but let me move on and then quickly discuss what we can say more in general. If you have no n parallel links, you can, that's the natural next step, then you can find another set of necessary and sufficient conditions. They are just less readable than they used to be in the case of 2. Okay, but still you can get something. For example, if you have this random variables that are independent from link to link, okay, it's sufficient that they are uncorrelated. This is the random variable uncorrelated, then you have no problems. The price of anarchy is, you can achieve price of anarchy 1 by implementing this policy. So if you have independent shocks, in this case, that works. And what's wrong with correlations? And you can analyze cases. Okay, if you have 3 parallel links, there was no correlation problem with 2 parallel links because you were only looking at the difference, and then you would get rid of that. But with 3, it's when you start having correlations. And basically, I will not go into the details, but you can find out why correlations are playing against you in the case of 3 links. And let me go quickly and just explain the kind of generalization you can look at. We generalize this to still affine delay functions and what are called linear independent network. Linear independent network means that every path has a link that belongs only to itself. So if you look here, there is this path E1, E5. E5 belongs only to that path. Okay, if you follow the path E1, E3, E6, there is E3 that belongs only to that path, and so on and so forth. So for those, they were considered already in the literature for other kind of results. And we have some optimality conditions on the linear independent networks. They look in a way similar to what before, but with some complications. And again, a key important role is played by the covariances of this term. And you can also create, so what you want is this covariances, and at the level of paths, you want some sort of monotonicity of the derivative of the functions. We can discuss it in detail if someone is interested. Let me wrap up. So I discussed 2 mechanisms that are relevant in transportation to reduce inefficiency. The first one was tolls. Okay, I looked in particular at dynamic tolls with this 2-scale dynamics. And the main result was that this feedback marginal cost pricing works in the sense that I explained. And it's a nice result because it's a global optimality and stability result with completely decentralized information. The second part, I discussed this information design in routing games, and I gave you some sufficient and sometimes necessary conditions for optimality in the case with affine delays. I think the main message is that in that case variance helps, correlation hurts. Okay, if you have to summarize it in a single. All right. We have several extensions. One thing I mentioned was the role of delay in the dynamic pricing. We have no theory, but I think that would be done. In the second set of problems, delay functions that are not affine, they pose different challenges, and also more general topologies besides linear independent. I can discuss heterogeneities. Okay, if there are two kinds of users that feel that time has a different cost, that makes the problem much different than it is in this homogeneous case. But of course, at the end of the day, one would like to see something that combines and optimizes the efficiency of the system in a smart way. Anyway, thanks a lot.
Well, thank you, Giacomo. Are there any questions? So we have time for one question, one short one.
One short, okay.
Why?
Thank you very much for the presentation.
Thank you.
Yeah. So when you talk about dynamic pricing, when you mean dynamic, like can it be instantaneous? Can you change the price dynamically? Or
You're talking about practical implementation.
Yes.
I should have mentioned that. Then you can. Then of course it depends on how quick you can implement that. But there is dynamic pricing implemented already with several restrictions. There are, yes, to make this results practical, I think there are all sort of details. You're saying how quickly can you change pricing, that's one constraint. How large can you make the price, that's another constraint. Perhaps you cannot touch all the links. Already in the static setting, if you cannot intervene on all the links, that becomes a very complicated problem, much more complicated than that. So what you're mentioning is, from a practical perspective, it's very important. Yeah, how quick can you update the links? And that's it.
I am Azzat, a PhD student in Florian Dörfer's group, as well as Emilio Fazzoli's group at ETH Zurich. And today I am representing Florian, who unfortunately could not make it today, and will be speaking about our work on something called karma. So the motivation is similar to previous work. We're interested in socio-technical control systems that have humans, that involve humans, and when these systems, because they involve humans, unfortunately as control engineers, we're always used about thinking about things like performance and efficiency, but with humans involved, there are many other societal and human factors that are important. Most pronouncedly, we argue is fairness. And as we've partially seen in some previous talks, many times efficiency in these systems, when you don't have interventions, they lead to inefficiencies, and efficiency is typically achieved using monetary incentives. And we think that's what makes these kinds of systems always be in tension between fairness and efficiency. We have here three typical examples where we think that there were different societal inclinations in this trade-off between fairness and efficiency. To the left is an example where there was a strong societal sentiment for fairness over efficiency. That is data networks, so like bandwidth allocation, and there are lots of seminal works by Kelly and others showing that something like the TCP control, a congestion control mechanism, which essentially runs the modern internet, converges to very fair allocations that split available bandwidth fairly. And you might recall the heated debate around 2015 about something called net neutrality, where there were some proposals to charge people differently based on how much they need bandwidth. And that kind of price discrimination led to lots of controversy that this would, let's say, jeopardize the free, like that the internet is a free and open resource for everyone. And there was strong public sentiment that we should not do that, we should not create internet fast lanes. The center example is in the transportation domain. And here we argue that things are a bit more, let's say, controversial or debated. So there are successful examples of where congestion pricing or monetary solutions have been implemented. For example, these charged lanes in the US. There is New York City congestion pricing, which is an interesting case because it took about 70 years of debate to finally put that through. It only came through earlier this year. And this is, and there was lots of lawsuits and so on. And so this is why we say that still the public is somewhat more in favor of fairness over efficiency in this example. And finally, the third example is energy, which at present is, well, largely monetary. There are electricity markets that deliver us the electricity prices. And that works well at the moment because these markets are highly centralized. So it helps achieve like the most cost-effective electricity to the end users. But we postulate that as these markets become more decentralized with renewables and so on, and users become more active end prosumers, the heavy reliance on money might also become controversial. So if there is one key point to portray in this talk, it is this. It's that, okay, there is this classical tension between fairness and efficiency, and I will hope to convince you today that these need not be in tension. Well, all we need is good karma. And this tension is really there when we look at these kind of resource allocation problem in single-shot and static ways. And actually there are lots of impossibility results, deep impossibility results that you cannot attain fair and efficient allocations in a non-monetary manner. There are some exceptions, including the information design, so when there is some information asymmetry and so on. But in general, it's pretty much impossible to attain fairness and efficiency in static settings. When instead we embrace, let's say, the fact that these systems are highly repetitive, so people don't need data, roads, or energy once, but many, many times. That repetition plus a clever design of dynamics actually enables us to do much more. And this time dimension essentially intuitively allows to let people play against their future selves and come up with new kinds of non-monetary incentives. And this is the core underlying principle of the idea of karma. We'll introduce a system that, let's say, budgets resource consumption over time using these karma tokens, and in which when users yield public resources, so act in a nice way, they gain karma from others that claim public resources, so act in a, let's say, selfish way. So this is the high-level idea. This talk will be centered about this karma idea, which we'll explore together on three main parts or quadrants. We'll first, in order to give you an appreciation for how this karma idea works, we'll dive into a running application of traffic congestion management, which is based on our transportation science paper. So I present here a classical transportation model, which is different from the one that Giacomo talked about, the traffic assignment model. This is instead the bottleneck model, which concerns a single arterial highway, let's say connecting suburbs to the city center, but has a time dimension in it. So intraday dynamics, so how people choose when to depart. And well, this highway has a limited capacity. So in this example, let's say we have 9,000 commuters that need to travel in the morning. The highway has some capacity, and with simple math, you can determine how long the rush hour will be. So in this example, it will be 2.5 hours long. So I'm here trying to represent both space and time. And so people departing at 7 a.m. will be shown here, and let's say the traffic builds up as we go to the left. And there's actually, due to this conservation of mass going on, there is a very nice flow that, in theory, people can take, in which they space out their departures evenly, and actually that would lead to no traffic. But unfortunately, this is not a game theoretical equilibrium, because traditionally, most people want to depart at a certain time. So let's say 8:30, for the sake of an example. So if this highway is in free flow, it will be a strong incentive for everyone to depart at 8:30, which is why this is not an equilibrium. What instead would end up happening at equilibrium is that people tend to prefer to be early than late. So there will be higher inflow than the capacity at the early hours of the rush hour, and then less later, and this will lead to a buildup of queues. The conventional solution to this problem, which is somewhat what the stall lanes try to do, partially, is a monetary one. So actually, there is a theoretically optimal toll called the Vickrey toll, which is pretty intuitive. So you can, if you charge a time varying fee to enter this highway, you can find a certain way to charge it that makes this desirable flow in equilibrium, and that is the social optimum. But of course, there are at least two problems with this approach. One, Giacomo and Nima probably solved, well, maybe in a slightly different setting, is how to determine these charges. So conventionally, that requires lots of private information about the value of time and so on of the users. However, there are ways to do it dynamically in real time. Although I am not quite sure if stability guarantees exist for the bottleneck model. It's non-monotone. The second problem, which we will focus more on, is this fairness issue. Because of course, people have different capacities and sensitivities to money. So what will actually end up happening is, everyone hates departing super early, but those that cannot afford the tolls end up being those ones. For example, this pure student versus this rich businessman who can always afford to depart at the nicest time. So here's how we can achieve similar efficiencies with Karma. We will not control the whole highway with Karma, but only partially. So we will split the highway into priority lanes and general purpose lanes, similar to these toll lanes that do not toll the whole highway, but just part of it. And actually, this has been shown to be more publicly acceptable, because at least there is still this free option. So inspired by that, we also split the highway. And now we will endow each user with some tokens called Karma that are non-tradable for money, so they are completely non-monetary. They are used to access to these priority lanes. And so imagine an interface like this where you choose when to depart, and as well as place a bid, and we will take the highest bidders that would fill the priority lanes without congesting it, and grant them access to those lanes, where everyone else has to use the other lane. So if you bid higher than your competition, you would enter the lane, but pay the karma you bid. Otherwise, you enter this general purpose lane, but in that case, you gain karma because at the end of each day, we would collect all the karma payments and redistribute them. So you can see how with such a system, everyone is a winner because you either gain priority or you gain karma that is useful to give you priority in the future. And this is the core idea of how we can jointly achieve fairness and efficiency, because it will allow people, yes?
The question.
Yeah.
So here by money you mean fiat currency, but not like as a means of exchange, because you can still implement this one with money or not?
By money I mean like euros.
Yeah, fiat. So,
no, like actual real money.
Yeah.
One can say that karma is a fake money.
Yeah, so that can be used in this.
But it's only used for this purpose and nothing else. So it's a self-contained, closed economy.
Yeah, but from an economic point of view, it is money. It's a means of exchange.
It depends on how you define money. It's not the global money.
Yeah.
It's a purpose-built economy.
Use it anywhere else.
Yeah, and this redistribution is also makes it pretty unique as well. Because I mean, you can view tax as redistribution, but it's not quite the same thing.
But I guess the question is, can I buy your car?
No. No, strictly no. So they're non-tradable.
That's
Because if I allow that, then we're back to the inequities.
Yes.
So that's the main philosophy, that it's purely non-monetary. So this is on a high level how we can gain fairness and efficiency. Let me give a preview of the Nash equilibrium of this thing, and I will tell you later how we define this equilibrium and compute it and so on. So this is just a preview, but let's say that commuters, now because we have this repetition, we can consider dynamic value of times or dynamic preferences. So these commuters are in a rush half of the times or not in a rush half of the times. Actually the karma equilibrium ends up allocating these priority rates efficiently to those in a rush, to those that are in a rush, because they play against their future selves. So if they get in here when they're not in a rush, they have less chances of doing it when they're in a rush. In order to predict what would happen under a monetary tolling solution, we need additional information, namely how the users value their time monetarily. And here is an example where we introduce this heterogeneity with respect to sensitivity to delays. So a rich person maybe can always afford to pay $10 no matter of their urgency, whereas someone who's not, who's more financially burdened is essentially never willing to pay much to save time. And you can guess what will happen under a monetary solution. The priority lanes will go to the businessmen irrespective of their true urgency, whereas the more financially burdened will end up always in the congested lanes. Of course, karma doesn't care about that and will, let's say, allocate based on your true time varying nature of urgency. So, So that was a preview of the kind of results we're going to see later, but now I jump to the next part of the talk, which is how we come up with these equilibrium prediction. And this is based on a class of games that we call dynamic population games, based on these two publications in Control Systems Letters, as well as Dynamic Games and Applications. So dynamic population games you can think of as mean field games. We like to call them dynamic population games for a reason that will be apparent shortly. But if you're familiar with mean field games, that's more or less what they are. We consider, though, discrete state and action spaces, because that helps with tractability. So imagine this karma game being played. It's a large population. So there are many, many users that have some private individual states and play some individual actions. So their state would be this tuple of urgency, so how badly we want to travel quickly today, which is now a dynamic process, so it's not a static thing, so it can evolve based on some private Markov chain process. So some days I'm on a hurry, some days I'm not on a hurry, and so on. And naturally the second state is this karma, for which we use non-negative integers. So we use integer tokens for karma, and of course that's dynamic because it changes based on how you play this game. The action in every time step of this game is a karma bit that is limited by how much karma you have, as well as in the example showed earlier, one you want to depart within the day. So when we aggregate all these private states and actions over society, we end up with something called social state, which maybe you've heard about, it's also called mean field, depending on which literature you're coming from, population games or mean field games. It's essentially a macroscopic description of what's going on in society, consisting of a pair of two things. The first one is this blue, is the state distribution. So that is the distribution of these private states. So, for example, the distribution of how the karma wealth, and a behavioral policy, which is a map from state to action, i.e. the bidding policy of the users. And for the sake of simplicity, we assume that users of, let's say, the same type follow homogeneous policies. But we could introduce some heterogeneities by considering different types. Then this aggregate measure goes back to the users as what essentially makes this setting a game, because it couples the individual Markov decision processes. So this is a dynamic game. People are playing against their future self, and so we must model it as a Markov decision process, which is coupled through this macroscopic quantity, the social state. And one note on notation, we use square brackets for discrete arguments or quantities, like the individual state and action, and round brackets for continuous arguments, which are this social state. Yeah.
So the urgency vector, is it like small n the days, or?
Sorry?
What's the small n?
That's just the number of urgency values. So we use discrete states, yeah, discrete states and actions. So the first result is that an equilibrium of this thing exists. And in particular, here's the definition of what we consider an equilibrium. It's called the Stacey-Nash equilibrium, and is a fixed point consisting of two conditions. Maybe I start with the second one, which is the more familiar best response condition. So this policy of the social state pi star needs to be optimal in the sense of the alpha discounted Markov decision process of itself and this other part of the social state. The new condition is the stationarity condition, which says that the state distribution at the equilibrium is stationary. So this here resembles the stationarity condition of Markov chains, but it's a bit non-standard. It's a fixed because typically, so P would be the state transition matrix, which typically does not depend on the distribution, but here it does. So we're looking for fixed points rather than, let's say, an open loop stationary distribution. But the good news is that this fixed point is guaranteed to exist under some mild assumptions. The first one is continuity. So these two components of the Markov decision processes, the immediate cost and state transition functions, need to be continuous. The second condition is what we call karma preservation. So you cannot be creating karma out of thin air. And this is where this redistribution comes in. This ensures that the set of state distributions of the karma distributions remains compact and allows us to invoke an infinite dimensional version of Kakutani to prove that an equilibrium exists. So that's the first result. A second result, which holds for this class of dynamic population games more generally, not just karma games, is that we can reduce this notion of Stacey-Nash equilibrium to the more standard notion of Nash equilibrium in standard population games. So if you might be familiar with this book, which is one of my favorite treatments of game theory there is, by Sandholm on population games and evolutionary dynamics. But there they consider classical static population games. So they're also played in a large population, but there is no this dynamic aspect of state. There's another aspect of dynamics, which is evolutionary dynamics of how people change their actions. And there are lots of tools based on this, on how Nash equilibria are reached and so on. So this is, we think, is a nice result. The main proof idea is that when you inspect the Stacey-Nash equilibrium, part of it resembles the classical equilibrium, which is the best response, but you just need to define payoffs as the state value, like the long-run payoffs. And then the other part was the stationarity condition, but you can augment the static game with like a nature kind players and make that the payoffs of these augmented population resemble the dynamics. And we think this is a cool result because it allows us to use evolutionary dynamics to compute these Stacey-Nash equilibria, of which there are many options with different convergence guarantees and so on. And it's an active area of research. There are more and more dynamics being proposed with better guarantees. So this is essentially how we compute equilibria in these games. And here's an example. This example is not exactly for the highway setting I showed earlier, but for a similar setting where vehicles interact pairwise to see who crosses first in intersections. It's just a bit simpler for demonstration. And this coincides with a pretty high discount factor of 0.98. And this simple IID urgency process where everyone is either lowly urgent or highly urgent with 50-50%. And this is the equilibrium bidding policy. And we can see that it is efficient in the sense that high urgency users bid higher than no urgency users. This is the stationary karma distribution, so the distribution of karma wealth. So each one of these is a karma state, and that's the frequency that both individuals spend in these states as well on an aggregate level. And from this equilibrium, we can deduce that the equilibrium is almost fully efficient in the sense that it almost always prioritizes high urgency, except for very few states like this one that has a pretty low probability where you might end up in the state and not be able to outbid the low urgency. So it's efficient only approximately, but it does pretty well. And this brings me to the next part of my talk, which will be the last. So I've been mentioning these words fair and efficient a couple of times already in this talk. We'll now dive a bit into what should this really mean. And I would say this is late-breaking results. It's pretty complex to define fairness. So I hope we agree that there are lots of different notions of fairness. It's a mess. Here is how we approached it. And the key point is is we have this novel dynamic or repetition aspect, and that allows us to do new things. So let's break it down. If we assume that everyone follows the same urgency process, so everyone, for example, spends 50% of the time at urgency 5 and 50% of the time in urgency 1, then it's straightforward in a sense, because we can just prioritize those that have high urgency, and that is both fair and efficient, because, well, people get it when they need it the most, and because everyone has the same dynamics, everyone will get their turn to have high urgency, so over time it's also fair. We can add a little bit of complexity. By now, we're still considering fundamentally homogeneous processes, but change the scales of urgency. And this somewhat resembles if we think of urgency as willingness to pay, this would resemble the rich person versus the financially burdened person. And for this, we postulate that what is fair and efficient should still prioritize high urgency, but in a scale invariant manner. So the scale of how you choose to express the scale of your urgency is a private thing that doesn't really matter. What we are trying to extract these dynamic, extract efficiency from the dynamics without, let's say, discriminating against someone. So fair and efficient in this case would be prioritizing high urgency in a scale invariant manner. Now it gets even trickier if we consider general heterogeneity. So say that some users have urgency 5 half of the times and urgency 1 half of the times. So they have high urgency relatively frequently. Other users have high urgency only a quarter of the times, and low urgency 3/4 of the times. But their high urgency is higher. So it represents some people that are fairly disciplined. So they are not often late, but when they are late, they really need a resource.
Maybe they get fired.
Yes. And we chose these two to have the same scale, in a sense that actually the long run average urgency is the same as these two. But again, scale doesn't really matter, because we'll be looking for a scale invariant motion. And actually here it's really not straightforward to determine how we should give priorities, because there's this intrinsic heterogeneity, what to do about it. And the natural generalization of scale invariance is something in the literature called interpersonal non-comparability. So we want to somehow give priorities without explicitly comparing these heterogeneous agents. And if you dig into economics, there is a very poor social welfare function that embodies all of this, and that is the Nash welfare function. It is scale invariant and does not do interpersonal comparisons, and in the homogeneous case, it will end up prioritizing those with high urgency. And so let me tell you a bit more about this function, which we think is a hidden gem of social welfare functions. Well, hidden in quotes because it's not so hidden. This is a classical social welfare function, but it's relatively understudied compared to, let's say, utilitarianism and so on. Although we think it's a really cool one that embodies both jointly fairness and efficiency in a natural way. So here's the definition of it. It's essentially the product of utilities. But in order to make this well defined, the utilities need to lie in the positive quadrant, for which we need to actually have a benchmark allocation, x tilde, that makes everyone worse off. So this term here resembles the improvement of each individual agent with respect to that benchmark, and we multiply these quantities to get Nash welfare. Why is this cool? Well, we have two independent motivations. The first one comes from social choice theory, a classical field in economics. And this function is actually quite special because it is the unique function, unique up to monotonic transformations, that satisfies some very basic efficiency axioms like Pareto efficiency without making interpersonal comparisons. So without explicitly trying to compare the utilities of people on a global scale. So in a way, it extracts the possible efficiency gains in a fair manner. That's the intuition. A second motivation comes from bargaining theory, and that's where the name Nash welfare comes from. By the way, this has nothing to do with the Nash equilibrium, but it has lots to do with Nash's other famous result, which is the Nash bargaining solution. So we can think of socio-technical control problems in a sense as negotiation or bargaining problems, because citizens must negotiate on which control policy to adopt. And in an example of congestion pricing, it took forever to come to agreement because maybe lots of people were feeling that it's unfair. If the negotiation fails, then this benchmark allocation has a natural interpretation as the status quo, or so it could be, for example, no control, like let the highways get congested according to equilibrium conditions. And the allocation that maximizes Nash welfare, which is the Nash bargaining solution, is pretty special. It's deemed by many economists as the fair compromise of bargaining. It has been shown to be the natural one when you let the bargaining be sequential, so people give offers one after another, or also if you let the bargaining be repeated, so with some reputation effects, it ends up being the one that's evolutionarily stable. So yeah, that is to say that there is lots going on for this function, and it deserves more attention. But if we look at it in action for our problem, so I remind you of our running application. So we're trying to allocate these priority lanes. And now this is an example with 4 heterogeneous urgency processes. These all have the same scale, or long-run average urgency, but are different in the nature of the dynamics. So for example, these kind of users always have urgency 2, whatever that means. This kind of users is similar to the one showed earlier, have urgency 9, pretty high urgency, but not that frequently. And these two are somewhere in between. And in order to appreciate this Nash welfare function, let me first show the utilitarian solution, the one that would minimize the sum of costs. And so this one assumes that we can perfectly compare these urgencies, right? Like this urgency of 9 is meaningful to this guy who actually never experiences it, right? We argue that this is not necessarily a good thing to do. So it would lead to allocating the most, so I'm showing here the allocation of these priority lanes over different departure intervals, where this T star is the most desired time, let's say 8:30 a.m. So that's when everyone wants to depart, ideally. So utilitarianism will treat these urgencies as comparable and allocate the best resource or best slot to this 9 and so on. But this would lead to essentially pricing out these guys. So they never enter the priority lanes, and subsequently they do not gain from this policy at all. Of course, this is sensitive to scaling, because if I change this 2 to 10, they will get the best slots. Here is what the maximum long-run Nash welfare looks like. I should emphasize that shown here and there are the long-run average costs improvements incurred by those agents, and it's important to remember that we are not trying to compare these different agents, so we shouldn't expect these to be equal. But for example, it's good to see that everyone manages to improve. When we look at the allocations here, they are quite interesting. We see that the red guys managed to enter the priority lanes as well. And if you compare this, imagine that something like this happens where you split each of the departure intervals or resources equally. That could be argued to be the fair solution. What ends up happening here is some kind of fair trading of these resources. So for example, these guys who are very highly urgent few times get a higher share of the best allocation in these few times, and in return, those guys that are always urgent or have the same urgency always get larger shares in less desirable times, and in a way it works out that everyone is happy. So we think this is a beautiful function that extracts the possible efficiency gains from the dynamics without in a fairness preserving manner. And this leads to our last result for today, which in the interest of time will only state the informal version. Feel free to ask me about more details. We actually managed to show that under some conditions, those station Nash equilibria of karma economies coincide with the allocations that maximize long-run Nash welfare. And this, so they inherit the same nice properties, and this is formalize what we mean by karma economies being fair and efficient. And with this, I'd like to conclude. So we hopefully we've convinced you about how karma economies leverage the time dimension and repetition to jointly achieve fair and efficient allocations in a non-monetary way. They are well-posed dynamic population gains in which a suitable notion of equilibria are guaranteed to exist. And this nice reduction to classical population games enables computation tools. And finally, they approximately maximize long-run Nash welfare, which nicely formalizes common intuition on what it means to be jointly fair and efficient. You can find more information on karma on my website. You might have noticed there is a missing quadrant, which is the outlook. So we think in the future, we've already started a bit in this direction with some works that are ongoing of practical implementation aspects of how a karma system would look like to the end users. So we've tried to do some behavioral experiments with real humans, and we've also investigated. I think an important problem is how to learn in these games, because so far the Nash equilibria we looked at are centrally computed, whereas you should not expect users to be participating in these real-time karma auctions very actively. So it needs to be automated on their behalf. So learning in these games is a big open problem. They are multi-agent reinforcement learning settings. One should not expect monotonicity, so it's quite a challenge. Lastly, quick advertisement for a tutorial session we're hosting tomorrow. I would like to invite everyone to attend, where we will cover some of this stuff in more details, but also more generally look at dynamic incentive schemes that, in a sense, leverage this time dimension to do new cool things. And we'll be happy to host Omar there, Carlo, as well as Heinrich Schnax, who's a behavioral economist. So there will also some behavioral, not purely theoretical aspects. Thank you for your attendance, for your attention, as well as my collaboration team and supervisors. And here I'd like to say thank you.
Right, thank you, Esat.
For instance, the maximum of the V's, the sum of square of the V's, and so on. Now, average consensus aims to calculate the average of the values of all agents. I denote this average by overlying V here, and capital N is the number of agents. So this is just aiming to compute the average of the various quantities that each agent has. And the challenge really is the fact that this has to be done, this computation has to be done in a distributed manner, and it has to respect the communication topology of the network. The problem is that not everybody talks to everybody. In fact, at each instant of time, each iteration, an agent can receive messages from a subset of the agents. We call that set the in-neighborhood of that particular agent. And it can only send information to a subset of the agents again, not necessarily the same subset. And we call that set the out neighbors of that particular agent. So we have to have an algorithm that sort of respects this distributivity constraint. Typically, the calculation of the average is done in a distributed, in an iterative manner, where at each iteration, each agent sends and receives messages according to these constraints. And keep in mind that even though the average appears to be like a simple computation, it's a primitive for a variety of other tasks, such as estimation, inference, diagnosis, optimization, and so forth. And also, if you look at this equation here, you can think of it as a linear combination of the values capital V that each agent has. This linear combination can easily be adjusted to be any arbitrary linear combination. So let me spend a little bit of time introducing some graph notation that would be useful for our analysis. So a directed graph or diagraph script G is basically a set of nodes. So the set of nodes is really the set of agents. So script B is basically our set of agents, and we said that we have capital N of those. And then script E is the set of agents. These are directed communication units. In particular, if I have an edge Bj, Bi, that means that agent I can send information to agent J. So in terms of this notation, the in-neighbors of node J is basically this set here, script Nj minus. It's a set of nodes that send information to node J. And the cardinality of this set is called the integrity of node J. I denote it here by Dj minus. And similarly, I can talk about the out neighbors of node J. Remember, these are the set of nodes that receive information from node J, and the cardinality of that set is denoted by Dj plus. That is the number of out neighbors of node J. Now, a typical assumption, actually, it's a necessary and sufficient condition to be able to compute the average in a distributed manner, is that the underlying diagraph is strongly connected. That means, I'm just reminding you here that for any pair of nodes, Vi, Vj, there is a path that takes you from Vi to Vj, Vi sequence of edges through some intermediate nodes, respecting the edges are taken with respect to the about time-varying connections using this notation. The idea is that instead of a fixed graph, a fixed diagraph G, I can have a sequence of diagrams of this form here. Basically, the set of edges, the set of nodes remains fixed. The set of agents is the same, basically. But the set of edges that describe the sort of interconnectivity between the different agents changes with time. So epsilon, script epsilon is changing at every iteration k. Now, let me talk about a particular way of computing the average in a distributed manner. This is the ratio consensus approach. The idea is that I have a fixed diagraph that describes my communication topology, and then each agent maintains two variables, the y variable and the z variable. Initially, these variables are initialized, y is initialized to the value that agent j has, capital Vj. Z is initialized to the value of 1, we will see why. And then at every iteration, there is an update of these two variables. The update is very similar, so let me describe the update for y. So the new y for node j basically depends on its previous y, weighted by 1 over 1 plus its out degree. And then it's the sum of similar values, yi divided by 1 plus the out degree of node I, received from every in-neighbor of node j. So if you think about it in terms of implementation, the easiest way to implement this is via some broadcasting. Basically, every node I transmits to all of its out neighbors this value here and this value here for the z iteration. And then the receiving nodes basically sum up all of these values as well as their own value weighted appropriately. And this sort of iteration keeps going. There are other ways that are possible. I'm not going to get into that, but you will see in a couple of view graphs what other choices might be there. Now, the important thing here is that to implement this, you would have to have each node VI be aware of at least the number of its out neighbors. So node VI should know its out degree di plus, which is not necessarily a given in a directed graph topology. So assuming each node knows its out degree, this is easy to implement. And in fact, it's also easy for us to see what happens, because if we write compactly the iteration in matrix vector form, basically we have the vector of the y values. So this is an capital N dimensional vector. And then that vector gets updated according to a weight matrix PC that gets multiplied on the right by the previous y values, the vector of the previous y values. This matrix PC is basically a matrix whose entries are either satisfy these constraints here. In particular, if we look at column J of this matrix, it's basically a column J of this matrix basically has weights that are either 0 or 1 over 1 plus the out degree of node J. And in fact, these weights are there for all the out neighbors of node J as well as itself. That makes the matrix PC column stochastic. And using this property, it's not very hard to show what I'm stating here. If each node looks at the ratio of its y value over its z value, so this is Rj of k, it is a function of each iteration k, the limit as k goes to infinity of this ratio can be shown to be equal to the sum of the y values at time 0 divided by the sum of the z values at time 0. In fact, the way we chose this initialization essentially guarantees that this is V bar. This is the average that we are looking for. And this is going to be true for all nodes each. And the only requirement really here is that the weight matrix PC is a primitive matrix. And in fact, the way we chose the weights here guarantees that PC will be primitive as long as the diagram G is strongly connected. So this is the ratio consensus approach. Just to give you an example, let's suppose I have this directed graph here. The matrix PC that we talked about is basically a matrix. Let's say column 3 corresponds to node V3. V3 has a single out neighbor, that's node V5. So its out degree is 1 plus its out degree is 2. So the entries that you see here are 1/2 or 0. And it's basically 1/2 for the entry that corresponds to node 5 and 1/2 for itself. And the sum of this is, of course, 1. Now, if I initialize this, the ratio consensus algorithm with these values here, I see here on the right, I'm plotting basically the ratio at each node as a function of the iteration k. The ratios behave in this manner. Very quickly, you can see that they converge to 2, which is the average of these values. Now, it turns out that this idea also extends to time-varying topology. Now, in the case of a time-varying topology, we said that the set of edges at every iteration is going to be changing. So that means that if we construct a PC matrix for the corresponding scripted GK, for the corresponding diagram at iteration k, we will get a different matrix at each time. So basically the iteration becomes an iteration of this form where the PC matrix is changing at every time step because the topology is changing, the set of edges is changing. The initialization of Y and Z is the same, and interestingly enough, I can still show that the limit as k goes to infinity of the ratio at each node is basically the same as before and still the average of the initial values. Now the only difference here is that I need to have some mild connectivity conditions on the matrices PC of k, or if you think about it on the set of graphs that I get over each iteration. There are many sufficient conditions that guarantee this convergence of the ratio to the average. Here I give you a simple one. Basically, you can find a capital K, that is the length of a window. And if you look at that window of that basically contains K graphs, if you look at the union of all of the edges in those K graphs, that graph that you get needs to be strongly connected, and that has to be true for every window. So if that is the case, basically, that is a sufficient condition to get this property here. Now, one thing that may not be as nice is the fact that to do all of this, you would have to know actually each node would have to know the out degree that it has at a particular time step. So every time the graph is changing, every node will have to know its out degree. And like I said before, it's not necessarily an easy task in a directed topology. Now, I want to talk a little bit about the random sum ratio consensus algorithm. So the random sum ratio consensus algorithm does the following. Basically, every node J maintains two random sums, the sigma random sum and the eta random sum. The sigma random sum corresponds to the Y value, and the eta running sums exactly the same for the z value. Basically, the running sums, from their name, it's just the sum of all of the values that node J is sending to its out neighbors over all iterations up to iteration K. Remember that this quantity here is what node J sends out at iteration T. So if I sum all of this from 0 to K, that means I'm summing up everything that node J is sending out at each iteration. And of course, these running sums can be obtained recursively at each iteration. So, at each iteration, each node is sending out the running sum values, and then each receiving node basically takes the difference of two consecutive running sums and updates its yj and zj values. So rho ji here under normal conditions is going to be the sigma I, whereas mu ji here is going to be the eta I. So, and of course, the rho and the mu are initialized to 0 in the beginning. The running sums initially are 0. So if you think about it, I have presented to you a very convoluted way of just doing the same thing as before. Before, if I go back, I said that we're going to be summing up these values over all of our ring neighbors to update the y value, and similarly, something similar for the z value. Here, to sum up all of the values that each neighbor is sending out, and then take the difference of two consecutive such sums. So basically, it's this value, it's this last value that node I was sending. So it seems like an unnecessary complication to do the running sum ratio consensus, but actually there are several instances where it has been extremely useful. So I'll show you one case. One case is when there are maybe packet drops in the network. So here, I assume that I have a fixed topology. So I have a set of edges that is given by script epsilon. But at each iteration k, only some of these links are active, so some of the transmissions are successful, the rest are basically packet drops. So then what I can do is I can have each node bj basically update the rho and the mu values based on whether or not it has received something from the corresponding name. So if something is received, then rho becomes the new sigma I. If nothing is received, then the rho remains the same as before. And for the self values, I'm assuming here that they are available because there is no transmission. So basically, all I'm saying here is that if there is no packet drop and you receive something, update the rho, otherwise not update. The interesting thing here, if you think about it, even if there are multiple packet drops, consecutive packet drops over a link, once a transmission is successful, the running sum that will be received will include also the previous packet drops. So at any given time, once you receive something from a node, you basically have everything that that node was trying to send to you all of this time. Now, the proof, of course, requires some weak connectivity conditions, and it's going to be stated in a probabilistic sense. So, for instance, we want each link to be active infinitely often. And an important thing in the proof, which I'm not going to talk about, an important thing in the proof is that the two iterations for the y and the z are coupled via the packet drops. So if there is a packet drop for the rho, there is also a packet drop for the mu. So in some sense, there is a single packet that contains both running sums If that packet is lost, both running sums will be lost. If that packet goes through, then both running sums will be successful, will be successfully received. So here's an example just to get a sense of what happens. My initial values here are 4, 5, 6, 3, 2. Here I plot running sum ratio consensus with no packet drops. And you can see very quickly the nodes converge to the ratios of the nodes converge to 4, which is the average of these values. If, on the other hand, I have a probability of a packet drop that is 0.2, that happens independently between links and different time steps, I get, again, convergence to 4, but it's slightly delayed. And in fact, if the packet drop probability is increased, this delay will be even higher. No, I mean, this example was actually based on the same diagram that I presented before, same connectivity, same set of nodes and edges. Now, let me talk about this local invariance condition that provides some sort of resiliency to this running sum ratio consensus algorithm. So, if I focus on the Y iteration, and something similar applies for the Z iteration, but I'm not going to repeat it. Basically, we said that the Y at node J gets updated in this fashion, where the rows are basically equal to the sigmas, the running sums, which are given by this situation. Now, the local invariance condition states the following. If I look at any node, and here I'm looking at node J, and if I look at any iteration K, this has to be true. Basically, if you look at this equation a little bit, you realize some sort of mass conservation condition. Basically, if you think of the Y value, the values as masses, basically the mass that node J has, plus all the mass that it has sent out to its out neighbors, minus all the mass that it has received from its in neighbors, has to be equal to its initial mass. Remember, this is the sigmas here are the total masses that have been sent to a particular out neighbor or have been received from a particular in neighbor. So in terms of a picture, what I'm really saying for node J is that I have the running sum coming in from each in neighbor, and I have the running sums going out from node Vj to each out neighbor. These running sums are the same in the running sum ratio consensus algorithm. And then I have the current mass at node J, and this condition has to be satisfied for all of them. So this is interesting now because I have a condition that is invariant, and I can use it in various ways. For instance, if somehow anybody, an in neighbor, an out neighbor of node J, gets access to these values, then that node can verify whether this invariant is true or not. And if it's not true, then maybe there is some problem in the network. Maybe there is a problem with node J in terms of the computations that it's performing. Maybe node J is malicious. But the fact is that if this condition is not satisfied, then you have detected an error. And in fact, we can go a step further and state the following. If this condition is satisfied for all nodes J, then if we allow the network to continue executing and there are no, the nodes will converge to the average of their initial values B bar. And that's not very hard to show, actually, because if we sum up all of these invariants over all nodes, we get the sum of the y values over all nodes. We get the sum of the yj values at times 0 over all nodes on the right. And then here we get these double sums that cancel themselves out. So basically, what we get is that the sum of the y values at time step k0 is equal to the sum of the y values at time 0, and the same holds for the z values. And of course, we know from the analysis of the running sum ratio consensus algorithm that if we start at k0 and run the algorithm, we will have to converge to the ratio of this sum over this sum, which is going to be exactly d bar. So in fact, Alejandro Dominguez Garcia, who is a close collaborator of mine, who have worked a lot on these things together, will be presenting a talk that sort of takes advantage of these local invariance conditions to perform, to sort of come up with a shadow banning technique for fault-tolerant averaging. That talk will be tomorrow afternoon if you're interested, in an invited session on security and resiliency for cyber physical systems. Now, just as an example, just to get a sense of what I talked about, I have this network here. This is the corresponding PC metrics for this network. The initial values, I chose them to be I for node I. So this, the initial value for node 1 is 1, for 2 is 2, and so forth. So the average is 3. Now the nodes run the running sum ratio consensus algorithm with this weight matrix. And the only problem is that node P5 misbehaves. Actually, node P5 misbehaves at exactly 2 points in time. At iteration 20, it adds 1.25 to its y value. And at iteration 40, it changes its y value by subtracting 1.25 from it. Okay? But of course, notice that even though this is a local change for node B5, that local change is going to affect everybody because of the distributed algorithm. So in fact, if I look at the ratios that the nodes have at each iteration, I see a picture like this. Initially, I have some transient. Very quickly, the nodes converge to 3, which is the average. At iteration 20, node 5 adds 1.25. So there is again a transient. And very quickly, the nodes converge to a new average, it seems. In fact, this is 3.25, which is the average that you get if you think of node 5 as having an initial value of 6.25. 5 plus 1.25 that it added. Again, there is a transient, and very quickly the nodes converge back to 3. So the error, if you like, that node 5 added showed up here, and then showed up, corrected itself when it subtracted the 1.25 value. And in fact, if you look at the local invariant, basically the local invariance conditions node 5. 1, it's always equal to 1, which is the initial value. This is the local invariance condition for node 2. It's always 2, which is its initial value. And then for node 5, we see that initially it's at 5. At time 20 it goes to 6.25. It remains fixed because node 5 actually doesn't do anything wrong after this point. And then goes back to 5 when node 5 corrects itself. So this is interesting because, first of all, it shows if I use this local invariant condition, it's easy to see that all other nodes are sort of doing exactly what they are supposed to do. In fact, if I check node 5 any time in this period, I will be able to tell that node 5 has done something incorrect. So these sort of ideas can lead to any time error detection techniques using this checking of the invariant conditions. Now, for the last part of my talk, I want to talk a little bit about how these ideas can be used for trustworthy distributed averaging. The idea here is the following. I have a fixed graph, I have a fixed set of nodes. But I have two types of nodes. I have a set of nodes that are trustworthy, so this is VT, and a set of nodes that are malicious, this is VM. The remaining nodes are malicious. So the problem with the malicious nodes is that they may enter incorrect initial values, and they may even do arbitrary updates in their computations to influence the outcome. So basically, the goal of the trustworthy nodes is to obtain the trustworthy average, which is basically the average of the values of the trustworthy nodes. So in some sense, I mean, the trustworthy nodes basically want to remove the malicious nodes from the computation. So, to abstract away the question of how do I find who is trustworthy, who is not trustworthy, I assume here that every node, in particular every trustworthy node, Vj, has access to a trust assessment about every other node Vi. This trust assessment I denote by Tij, and basically it's supposed to be 1 if node Vi. And if I have this condition hold, this assumption here, if the diagram that I get when I focus...
You have 5 minutes.
Yes. Yeah, thanks. Okay, I think that should be okay. So if I focus on the induced graph that I get by focusing on the trustworthy node, if that graph is strongly connected, then I can basically run the algorithm on that induced graph. I mean, what I'm saying here is very simple, right? If I have this graph here, and node V5 is not trustworthy, and every other node here knows that, then basically these other nodes can remove node V5 by basically running the algorithm without taking node V5 into effect. Anything that they receive from node V5, they ignore. They don't incorporate node V5 in what they are sending out. So basically, the remaining nodes, if they know that node V5 is not trustworthy, they can run for example, the ratio consensus algorithm, not using node V5 in their calculations. Now, but the challenge is the fact that these trust assessments may not be available before we start the computation. And in fact, they may also become known at different points in time for different nodes. So here, I'm assuming a convenient setup where I have time-varying trust assessments. So Tij of k is available at every iteration k. It's either 0 or 1 to sort of indicate whether node j trusts node I or not. But the only assumption is that there is some finite time after which these trust assessments correctly reflect the status of a node, at least for the trustworthy nodes. So if Vj is a trustworthy node, Tij of k has to be 1 if Vi is trustworthy or 0 otherwise, at least for k larger. So eventually, trustworthy nodes know whether somebody is trustworthy. So the idea here is that I can use a time-varying version of the running sum ratio consensus to exclude and include nodes in the computation. So basically, the time-varying out degree of node J will depend on whether or not a neighbor of node J is considered trustworthy or not. And then, depending on this trustworthy out neighbor number, the running sums sigma and eta that we talked about before will be updated with the time varying out degree. And then the idea, and I don't think I have too much time to go into the details, the idea is that there are 4 different cases that we have to handle while executing basically the running sum ratio consensus that we talked about before. These 4 different cases are basically depending on whether an in neighbor or an out neighbor goes from trustworthy to untrustworthy or from untrustworthy to trustworthy. So that's how you get the 4 cases. Let me just talk about one of these cases. So case 1, the trustworthy out neighbor becomes untrustworthy. That basically means node VL, who is an out neighbor of node J, has TLJ of k minus 1, 1, which means it was trustworthy and then it became untrustworthy. So basically what needs to happen now is the following. Node Vj has been sending running sums to this to this out neighbor VL because it was considering this out neighbor to be trustworthy. Now this out neighbor is known not to be trustworthy. So basically, everything that node J sent to this guy has to be recovered. And the easiest way for node Vj to do that is basically divert everything back to itself. So Yj becomes Yj plus the running sum that node J has been sending out to its outliers. And the same happens, of course, for the Z value. And in fact, case 1b is the reverse case, when trustworthy out neighbor becomes trustworthy. In that case, the reverse needs to happen because node J was considering that it was not sending values to this out neighbor, but this out neighbor was, of course, performing the computations because it was receiving the information, etc. Now this out neighbor is passing the computation, so node J has to adjust it because this out neighbor is incorporating values that node J was thinking that they were not being incorporated. Anyhow, there are also the cases for the in neighbors. Those are in fact a little bit easier because essentially what happens is that you ignore that in neighbor once it becomes untrustworthy, and you subtract all of the running sum values that you have received from that in neighbor thus far. As an example here, I have the graph that I gave you earlier. Node V5 is the malicious node, but the other nodes do not find out about it until iteration 21. And before that time step, I'm assuming that the trust assessment values are basically random variables of 0 or 1 with, I think, with equal probability here. So you can see that the ratios do not really converge before iteration 21 because the trust assessments are changing things all the time. But after iteration 21, once the trust assessments settle to their correct values, the ratios converge to, I guess, 2.5, which is the average of the values of the trustworthy nodes. Okay. Now, the proof for this sort of things can be done also using these local invariant conditions that we talked about.
Chris, sorry to interrupt you.
I'm not going to go through the proof. I was about to say I'm not going to go through the proof. But you can read about it in the reference that I provided in the beginning here. here. It's a tag paper by me and Alejandro. So that's all I have to say. I put up the concluding remarks view graph, but I don't really have to talk about it. Thank you very much.
So the things which we possess in common are more numerous and more important than those which we hold in private. So we live in the era of sharing. Everything is sharing: bike sharing, auto sharing, car sharing. Give me ideas. Food sharing, co-working spaces. So the example I want to start with is electricity storage device sharing. So we have 3 people on the right, and they share a battery. And then we have 2 people on the left, they have their own battery. So I need your help to identify a couple of advantages. So give me a couple of advantages why sharing a battery should be rewarding, helpful. Just a couple of ideas, and then we go on.
Can you also charge the battery?
Yes, you use photovoltaics and you charge the battery in one direction, and then you take energy when there is no wind or no solar power.
There's a high infrastructure cost for batteries, so you can.
So that's the disadvantage. Oh, you mean
in
this case?
Advantage of sharing. You can. It's much cheaper to share a big battery than to have individual batteries.
And more flexibility sometimes if you are holding parties.
Very good. You just picked on 2 on the 3 categories of advantages that I listed here. So cost efficiency and grid stability. We also have some advantages in terms of environmental impact. So think whatever you have in mind is maybe classifiable in one of these 3 cases. So what is the role of coalitional TU games? TU is transferable utility games. So in this context, coalitional games with transferable utility, they provide an analytical tool. They provide a set of tools to assess the benefit of aggregation. So if we are together, what is the value? Okay? So in some sense, we can say that the value of coalition 1 to 3 is 100, and the value of player 4 alone is 10, and player 5 alone is 5. That's for the analysis. We want to design something, so imagine that the cost for maintaining the battery are entirely charged to the last player. We might say at some point, okay, it's no longer rewarding to stay in the coalition. I want to quit. The coalition is not stable over time. In this context, coalitional games with transferable utility provide a tool for designing incentive for this not to happen. So we want the coalition to be stable over time. Think of this like the counterpart of a Nash equilibrium. In a Nash equilibrium, nobody has an incentive to deviate in terms of strategy. If you allocate in a smart way, according to the core, there is a concept, then nobody has an incentive to quit from the coalition. Okay? You agree with me that saying that the value of a coalition is a number is an oversimplification. So in reality, the value of a coalition is something that changes with time and will depend on some decisions made by the players. They can agree on some decisions and they can influence the value of the coalition. And also it might depend on some uncertainty. So if we are producing energy from the wind, we don't know how much wind is tomorrow. So that's the energy. Or if we are selling a product on the market, we don't know the market demand tomorrow. So the value of a coalition is a function of the joint decision and of the uncertainty. In this uncertain scenario, the idea is, because everybody makes always the assumption that players know how to optimize their joint decision. So we want to drop this assumption. So the players, they get together and they play naively, okay? But they are smart. They have some sort of learning mechanism, so they know how to improve their joint decisions. But the game is running, so they get together, they create a value, they allocate, and they get smarter. And I want to bring both elements into the topic today. So you see in the title, we have 2 elements. One is the gradient dynamics, which is accounts for the learning part. And the second one is coalitional games with transfer utility. So people get together, create a value. We want to assess the value of staying together. So
Good afternoon, I'm Dario Bauso. This is a joint work with Azim Khalegi, my PhD student, and with a colleague from KU University, Toru Nagikawa. I assume that not everybody is familiar with TU games. Can you raise your hands if you are not familiar? Okay, so do you agree that I will spend just 5 minutes to give you the basics, and then we jump into the today's work? There is one misconception I want to start with. So because people look at cooperative game like an alternative approach to non-cooperative. So for some people, cooperative game means all of the sudden the players are interested only in the social welfare. They are no longer selfish. That's wrong. Even in a cooperative game, players are super selfish. They cooperate, they stay in a coalition only if they have the right incentive to do so. Okay, so players are selfish. And how does a typical model look like? So what is a coalitional TU game? It's a set of players, and it's a characteristic function. This takes place in the power set. This is the set of all sub-coalitions of n players. Okay? And it returns a real, the value of that coalition. How do these incentives look like in this context? Well, we can allocate maybe according to the imputation set. This is already something. So we might consider to allocate to each player at least as much his own value is. So if I get less than my own value, B of I is my own value. If I get less than my own value, I will quit. I say, okay, it's better for me to play alone than stay in the coalition. And this is called individual rationality. What we allocate is the budget we create. So this is the value of the grand coalition. This is the added value of playing all together in the grand coalition. And this is called efficiency. So any allocations vector, so we're talking about n-dimensional vectors that are efficient and individual rational, they are in the core, in the imputation set of the game. So the imputation set is the set of allocations that satisfy these two properties. Still, we don't have any guarantee that sub-coalitions might be more rewarding than the grand coalition. So I might join with just another player and getting more rather than playing all together. For this not to happen, we have to introduce a third property, which is called stability with respect to sub-coalitions, and it's also it's a linear inequality. This is going to be a polyhedral set. So the total amount given to any member of the coalition, for every coalition, has to be not smaller than the value of the coalition itself. Any allocation which is efficient, individual rational, and can guarantee stability with respect to sub-coalitions is called in the core of the game. So what is the core? Is a polyhedral set that guarantees the three properties listed here. So if we allocate according to the core, then we incentivize people to play all together in the grand coalition. Nobody has an incentive to deviate. Do you see time playing any role so far? No, everything is static. Coalitional TU games, they originate in economics, right, in the 60s. So there's no time, it will come later. A few facts about the core. Some of these facts are more or less known. So the core can be obtained by solving a linear program. That's a good news. We solve a linear program, we obtain any allocation in the core. In order to see how this can be shown, let's order the set. So now we have an ordered set of subsets. And this is the index set, 1 to n. So from now on, sometimes instead of saying for all coalition of n players, for all sub-coalitions of n players, I will say for every j in n. For every j in n means I'm taking into account all possible sub-coalitions of players. I'm introducing some vector notation to see how the LP program will look like. So now, consider any coalition and consider the characteristic vector. It's an n-dimensional vector that says 0, 1 if the player is in the coalition or not. Okay? Take this vector, transpose, and pile all these vectors in a matrix B. I will show you an example, you will see, and it will become all of the sum here. So you have a matrix B. now pile up all the value of the coalitions according to this sequence in a vector B. So the jth entry of this vector is the value of the jth coalition according to this ordering.
Maybe you'll comment on this, but there is a combinatorial number of codes.
Yeah, the sequences. You mean but it's arbitrary, but it doesn't make any impact on the results. So the ordering doesn't influence the.
But there are so many of these. If there is.
I mean, this is m is 2 to the power of n.
Yeah.
You're right. 3 players, you have 7 collisions. 4 players, you have 16. So it grows exponentially. That's a problem for the LP. You're right. So when you solve the LP, it's linear, but you have an increasing exponential number of constraints. That's the point. Yes. Sometimes when you have too many players, you randomize. You pick randomize. You randomize the collisions. So this is approximation of the core, but that's another story. Okay, not for today. So this is how it looks like for 3 players. So if you have 3 players, this is the total amount that you allocate, and you want to make sure that player 1 gets more than V1, player 2. These are the characteristic vectors. Player 1 plus player 2 gets more than V12, and till x1 plus x2 plus x3 gets at least V of the grand coalition. What do you see here? You see the left-hand side of the last constraint is indeed the objective function. So you are minimizing, and then you stop if we are lucky, and I will tell you why we need to be lucky, and we stop when we reach this value here. If the optimum of this guy is bigger than the value of the grand coalition, it means the core is empty. So there's no way to allocate the value of the grand coalition and give and satisfy individual rationality and stability with respect to subcollisions. So the non-emptiness of the core means the optimum of this LP is exactly equal to this guy here.
These values are pre-computed?
Yeah, at the moment we assume that these guys are known because we are still in the preamble. Okay. Later, when we talk about the current paper, this becomes stochastic. Yeah. Okay, but this is a classical TU game concept. Okay. So this is the condition for the core to be non-empty. And now you think, okay, the people usually calculate, they solve the linear program. No, people, they look at the dual. So usually people, they solve the dual, which looks like the blue LP problem on the right. This should be a less than or equal set of constraints. You are maximizing, so at the optimum, they are satisfied with equal side. And this condition, this set of equality, are used to introduce the concept of balanced map. So when you say this map is balanced, is actually satisfying the duality constraints, this problem here. Okay? And then we know from weak duality theory, then the dual problem needs to provide a lower bound for the primal. Okay? So if this is true, we say that the game is balanced. So all these new concepts, actually, this is just duality theory. Okay, indeed, if you implement these 2 concepts, then you find the famous Bondareva-Shapley theorems. We go back to the 60s, and they state the equivalence between the core to be non-empty and the game to be balanced. They are just using duality theory. Okay, and I want to emphasize this because we are going to prove that the game is balanced using the concept of balanced map, a balanced game. So that's it's not only just a preamble, but these are tools that we are going to use later. So what does the Bondareva-Shapley theorem says? It says, give me any balanced map, duality constraints, and make sure that this inequality is always true, weak duality theory. And this guarantees that the core is non-empty. So there is a way to allocate and make everybody happy to stay in the ground coalition. There is one last concept in terms of basic concept, and then we move to the current paper. It's the one of Shapley. Are you familiar with the Shapley vector? Because Shapley is very, very popular among economists. Okay, because it has a lot of nice properties. You don't know the concept, but you know the idea behind. We allocate proportionally to the marginal contribution that the player brings into a coalition. If a player joins a coalition and the coalition is 10 times greater, he will get 10 times greater allocation. Okay, so the idea of marginal contribution is at the foundation of the Shapley vector. How do we formalize everything? So imagine the grand coalition is formed sequentially. So we play all together, we enter this room in a given sequence, so we create a coalition according to a specific sequence, sigma. Why do we need sigma? Because then the inverse of sigma tells who is already in the coalition when I join. This is the set of predecessors. And if I know the set of predecessors, I can calculate what is my marginal contribution. If I'm player I look at the value of the coalition without me, and with me, the difference is my marginal contribution. And this is for every player and for specific sequence, sigma. Now we do the calculation for all the players, so we get a vector, and this vector depends on sigma. We average over all possible sigma and factorial, so we have a lot of potential sequences. We do this huge averaging, and this is the Shapley vector. And this is how people usually calculate the Shapley vector. It's just the averaging, sum, okay? But there is a very interesting property that we are going to introduce, we are going to exploit later, that the Shapley vector actually is a linear function of the vector of coalitions values. So the Shapley vector as a linear function is less exploited property. So essentially, give me the vector of coalitions, and I can find a matrix. This matrix depends only on n, the number of players, and I know how to allocate according to the Shapley vector. Is this an interesting property? Yes, because if v depends on time, then we can create a recursion, right? So this is how it looks like for three-player players. Okay, this is the L matrix. Why is this interesting? Imagine you are given a sequence of coalitional games. So now the value of the coalitions change over time because of the decisions and because of the uncertainty. So we can introduce a recursion on what? On this guy, this is the surplus vector. And we know that the surplus vector needs to be non-negative if we want to be in the core. The surplus vector is the total amount given to the member of the coalition minus the value of the coalition. We know that this guy cannot be negative, because if it's negative, that coalition will quit. Okay? So this has to be true at all time, but sometimes we don't know this guy. So we want to allocate, but we have a imperfect knowledge about the value of a coalition. So maybe we try and error. So we create a recursion. With this recursion, I'm capturing the patience of the players. So it can happen that at a specific time t, this guy is negative, some of the entries, which means somebody might have an incentive to quit the grand coalition. But we can prove that asymptotically, this vector will converge to a point in the positive overtant. So that means be patient, play the game all together, and you will get more than if you quit. Okay? So let me just emphasize that, of course, you have discrete time and continuous time version. The connection between coalitional Q games and dynamical systems was not there up to a few years ago. Okay? Then I met this lady. She's in stochastic operations research, and then we thought, okay, maybe there's a way to create a nice connection. And then there is also literature on coalitional control. Mostly people from Seville. They are playing a lot with this idea of coalitional control. Any questions so far? Yeah.
So I think that the competition of Shapley is Nash. Right?
Okay.
Nash bargaining.
The counterpart. Yeah. Okay.
Have you thought about that direction?
You mean the analogy between Nash and
So I think that the main two classical solutions for coalition games, or I guess it's related to wargaming as well.
Okay.
It's Shapley or Nash. So Nash has a bit different properties, but also nice ones.
We can discuss maybe later between the analogy, because in a classical TU game, Nash doesn't appear, doesn't play a role. But if you calculate the value of a coalition as an imp soup, so you take the maximum with respect to the joint action of the members in the coalition versus the worst case with everybody else outside the coalition, then Nash plays a role. But that's a computational way of calculating the value of the coalition. But we can talk a bit later about this connection. So let's look at the problem I want to share with you today. Are you familiar with the news vendor? The news vendor is a typical okay, this is a news vendor style problem, okay? So a lot of things we know. You recognize the news vendor payoff function. So you have different players. Every player faces an uncertainty. Think of the uncertainty like the market. I is the market, the ith market is uncertain. And they can aggregate. So US is the aggregate market. Aggregation means sum in this case, okay? And this is a typical profit. The profit grows with the offer. So the joint action is how much we offer on the market. So the revenue grows with the offer, but we pay a penalty every time for every mismatch from the market, from the uncertainty. It's a sort of track the uncertainty game. So if you know U, the best you can do is X equal U. But if you don't know U, because you have to make a decision in advance, then you have to try your best guess for U. Okay? So it's a very general, simple framework. And actually, you can show that when you bring multiple wind producers together, it looks like something like this. This is how much you bid today, and this is the penalty you pay if you are delivering less or more energy tomorrow. Okay, so this is a stochastic, because this is stochastic. And then we say that the value of a coalition is the expected profit. So we take expectation with respect to the uncertainty. So we have the revenue minus the expected value of the overshooting or undershooting. So in expectation, how much we pay if we deviate from the market. So it's a decision making under uncertainty. So what do we do with the uncertainty? So we say that the aggregate uncertainty is the sum of the individual uncertainty. It looks like a very simple assumption. This is really fundamental because it's the law of large numbers. We aggregate uncertain stochastic processes and we filter out fluctuations. So it looks like a very simple assumption, but it's also at the basis of some of the results we obtain. Another assumption is that the distribution of the aggregate uncertainty is lower and upper bounded. We are going to use the lower bound to prove a strong concavity. We are maximizing, so we like the idea that this function is strongly concave, and this is actually because of the lower bound on the probability distribution. And then we are going to use the upper bound to prove Lipschitz smoothness. The two properties, they are useful because then you take the second order Taylor expansion and you find an interval, a lower bound and an upper bound for the function. We are going to use both properties to prove the linear convergence of the algorithm. Okay, so at the moment there is no time because there's no gradient dynamics at the moment. We just have a game, but we want to know what's the optimal value of each coalition. So what is the best the players can do when they join together? And in order to know this guy, we need to know this guy. This is the optimal joint action. Okay? The good news is that this function is strongly concave, and therefore we have one unique optimal joint optimal solution. And this is obtained from the critical fractile formula. This is the news vendor, okay? So this guy is usually something between 0 and 1. Suppose it's 0.8. Then you want the value x, whose cumulative distribution function returns 0.8. This is the inverse cumulative distribution value. Nothing new. This is just the news vendor approach, okay? For the static analysis, it's useful. Still a steady state, no dynamics so far. We can say that if the players, they play optimally, so in the ideal situation where everybody knows how to optimize the value of the coalitions, the game is balanced. And we are going to use two properties to prove balancedness of the game. One is Superadditivity. Superadditivity means take any two solutions, any two coalitions, disjoint. The value of the union is not smaller than the sum of the value of the original coalitions. This is superadditivity. We say that the game is superadditive if this property holds true for every pair of these joint coalitions. And then we use positive homogeneity. Well, there is a way to formalize, but the concept is if the uncertainty scales up 10 times higher, the profit scales up 10 times higher. It makes sense. If it's market demand, if you have a much higher demand, you assume that the profit is going to increase proportionally to the demand. In formulas, essentially you take the optimum of the expected profit and you make it explicitly dependent on the uncertainty, and then you put here the factor, the scaling factor. If this guy goes up and down, the profit of the scaled uncertainty is actually obtained proportionally from the profit of the original uncertainty. So that's the concept behind positive homogeneity. Yeah? In the next slide, I want to show how we can use these two properties to prove the balancedness of the game. So you will see again the property we showed at the beginning. The value of the ground coalition needs to be greater than or equal every combination of the value of the subcoalitions weighted with the balance map. You remember this is Bondareva-Shapley theorem. And we have a sequence of equality, but we can use positive homogeneity to bring the balance map. Before it was called lambda, now is alpha. It's the balance map. So to bring the balance map inside the optimal profit. And then we use superadditivity to bring the sum inside the optimal profit. So, and then we can prove that the game is balanced. Okay, so eventually we have time. We have time playing a role in our setup. So you remember I told you the players are naively playing at the beginning. So they don't know how to optimize. They just play, but they get smarter and smarter. How do we capture this capability of getting smarter and smarter? It's just a discrete dynamics. It's a gradient dynamics. So they play in X. They look if they can improve. This is the step size, and then improve at the next iteration. If they know in advance the distribution of the uncertainty, so they have a priori knowledge on the distribution, they know how to calculate this guy, the expected profit. So this dynamics is deterministic. Later it will become stochastic if there's no knowledge of the distribution. Okay, but so far, assume they know the distribution, they know how to calculate B, so this is a deterministic deterministic gradient dynamics. So they calculate the gradient, and we can also write everything in terms of the recursion in the coalitions values. We have a dynamics, so we want to answer two questions. What questions do we have? A dynamics. What do we want to know from a dynamics? Equilibrium points and convergence. Okay, this is what's happening now. So first, the equilibrium point. The good news is that because of some assumptions, the joint optimal is also an equilibrium point for these dynamics. So it's the joint optimal, but it can be also obtained as a unique equilibrium point for the gradient dynamics. That's straightforward. At the optimum, all the gradients are zero. Convergence. This is a little bit more entangled. We need to go through Lipschitz smoothness, and then I will prove convergence at the linear rate. And I will give you a couple of ideas. So again, we need some vector notation. What I'm doing here is exactly what I did before. So I ordered the coalitions, and then I stuck all the decisions or the joint decisions of any coalition in a vector X. But now times plays a role. So this is a time-varying vector. So this is the selection of all the joint decisions over time. I do the same for the optimal joint decisions. I do the same for the coalitions values, and I do now the dependability through the decisions of the players, and I do the same for the optimal of the coalitions values. So you order the sequence, you bring everything in a vector or in a matrix. L smoothness, essentially what I'm saying is that for every coalition, this function is Lj smooth, because it depends on the coalition J. What is this? It's actually an upper bound on the second derivative. Okay, so with L smoothness, what we have is that if we approximate using the second order Taylor expansion, if we approximate the function in the point y, then what we get is a lower bound of the function itself. Okay, so that's the usefulness of this assumption. And now you want to know the main results. This is the main results. Convergence is at linear rate to the optimum. So this is a convergence in the iterates. So people are improving, getting smarter and smarter. And for every collision, they will converge to the optimum of that collision. And convergence is at a linear rate. Why linear? You take the limit for t going to infinity of the left-hand side, and then you get something which is between 0 and 1. And that's the shrinking rate. That's the linear rate. I'm sure you want to know how we prove that. It's technical, but I will emphasize the ideas, okay? So don't get lost in technicalities. This is the guy we want to shrink to 0. That's the distance in the iterates. For every collision, the joint decision at time t minus, detracted from the optimum. So we prove this for every collision. We replace this guy using the gradient dynamics. We expand the square. So we get 3 terms. The blue one is the cross term. We use strong concavity to replace the blue terms with a minus lambda mu j square term, minus 2 lambda, the value at the optimum, and the value at time t minus 1. Now I'm collecting together the red and the blue, and I'm using the Lipschitz smoothness to upper bound the red. And the red and the blue together, they yield this term here. And this term is nice because it's non-positive. So then we can drop from the inequality, and then we are left with this guy. This is the distance at time t from the optimum in the iterates, is upper bounded by this guy here. So this is a relation between 2 consecutive times in the algorithm, t minus 1 and t. And we telescope, and then we obtain the linear convergence rate. So that's the idea. I just want to give you the ideas. So L smoothness and strong concavity, and we have linear convergence. Questions? Okay. So then we move to the last part, which is about what happens if people don't know the distribution. Okay, we made an assumption about everybody knowing this in advance, but if you don't know the distribution, then you can only play the game and randomize and see what you get. And this is the idea. So we have a batch of samples. We replace the expected profit with the sampled average. And we use this guy. So ideally, we would like to have the gradient of this guy. This is what we want to use, right? But we don't know this guy because we don't know this the distribution. So we can replace this guy. This is what we want. We can replace with this guy, which is an unbiased estimator. So if you take the expected value at time t of this profit, this is the profit you get at time t by playing. So you play and you see some profit coming. Okay, so this is your random profit. The interesting fact is the expectation of the gradient of the random profit is equal to the gradient of the sampled average profit. Okay, so then the gradient dynamics becomes stochastic because this is the expected profit, and these are the decisions. They are also stochastic. Everything becomes stochastic, so we can prove some convergence properties, but in expectation. Okay, so this is exactly what happens. To prove the convergence in expectation, we use the boundedness of the variance. So everything is stochastic, but there is a good news. The variance is bounded. So this is the upper bound in the variance, and this is going to appear in the step size. So we design the step size of the algorithm, taking into account the information on the upper bound of the second moment. Okay, so what we prove is that this is the sample average profit at the optimal, and this is the expected value of the sampled average profit calculated considering the sampled average on the decision. Okay, this guy is stochastic. We take expectation and we prove that these two guys, they converge. And convergence is at sublinear rate. So we take the limit for of the right-hand side, and what we get is 1. Okay, so we put less information means slower convergence. That's quite intuitive. So now the question is, we played a lot with these convergence properties in the coalitions values. How do they translate in terms of staying in the coalition is beneficial to everybody? Because that was the original question, right? We want to stay in the coalition and get the right reward. You see, everything here depends on B. So if we have some interesting properties in B, they translate into properties in the surplus vector. So essentially, we build on the convergence results in the coalitions vector to prove that in the long run, asymptotically, everybody is patient, the surplus vector will converge to the surplus obtained when you allocate according to the Shapley vector at the optimum. So this is actually translating in terms of benefit of aggregation all the preceding all the previous results on the function B. Okay. We know V. If we know the distribution, we know V, so we can allocate. But if we don't know the distribution, same story. We allocate according to the stochastic profit. So now even the Shapley allocation is stochastic, because this is the random profit at time t. We have a stochastic recursion on the surplus. And then what we can prove is convergence in expectation. Okay, so the expected value of the surplus vector converges to the optimum. So we talked a lot about collisional Q games, convergence. Shall we look back at the original example? It's nice to have a look. So it's with a new awareness that we can look at this example, and we can also recognize the versatility of some of the ideas we shared. So imagine that this guy is now the grid. Okay, it's not a battery, it's just the grid. And imagine that the uncertainty is the solar or wind source. And imagine that these are prosumers. So every day they are in the market and they bid. And they have to find their optimal bidding, but at the beginning they don't know what's the optimal bidding. They just play and try to improve. And what is the dynamics? The dynamics captures this capability of the players to improve their way of bidding in the market. And what is the convergence? It's a long-term incentive for cooperation. So if you converge, then you have guarantees that in the long term, playing together is more beneficial than playing alone. So that's how we can interpret. And before I conclude, this is the advertisement moment. The ideas I shared with you today, they are going to be in a new book, which is coming, and much more in a new book, which is coming very soon. I hope in September it's going to be finalized. It's going to be published for the SIAM, the series in Advances in Design and Control. It's jointly with Tamer Bashar, and the material is already there, 250 pages. Usually when you open a book in game theory, you have 90% of the material is non-cooperative and 10% is cooperative. Well, we reverse. So up to chapter up to chapter 10, this is going to be coalitional Q games. So the idea of designing incentives to have people cooperating. And then from chapter 11 on, then this is the non-cooperative part with the Stackelberg game, reverse Stackelberg game. And that's pretty much it. Thanks for your attention, and I'd be happy to take any questions you have.
Thank you, Dario. Are there any questions from the audience? I might have a question. So I can't remember. I couldn't see the slide number, so we have to go back a bit. You showed before the Shapley value dynamics. Yeah, so this one here. So you mentioned that G is this variance that you have.
Yeah, it's an upper bound on the variance.
Yeah. So, so it does seem that if your variance is larger, your step size has to be a bit smaller, according to what you have calculated there.
Yes, yes, I agree with you. According to this rule, is it counterintuitive?
Yeah, that's what I hope to discuss. So it says that for as time goes further, your step size has to be smaller and smaller. And then it's also dependent on the variance that you have. So yeah,
I agree with you that this is how I interpret also this rule, which to me makes sense, because if you have a lot of uncertainty, you cannot wait too long, because then it becomes unpredictable. So it makes sense, but there is also a G here in the numerator of the upper bound.
I see.
So you want to see the disruption coming from G. I think the disruption is here, because a higher variance, then you have a higher upper bound in the deviation.
Yeah, and then as time goes further, you also have to take smaller step sizes.
Yes.
That seems a bit counterintuitive to me. Well, the G I agree, but then with T, but it comes out of the calculation. So
it's counterintuitive, the square?
With the step size, yeah, there.
Okay.
Yeah. But anyways,
okay, that's interesting. I will think back about this. Okay, so you would it would make more sense the step size to have a.
Yeah, because what you have as a guarantee is that as time goes, as you evolve in time, your expectations actually converge. So I would expect that the step size would have to be, well, you don't have to take so many step sizes to get there. Well, but then that's just intuition.
Okay, but thanks, it's quite enlightening. So I will be thinking about this. Thanks, Michelle.
As far as I understand, you start at the end, you said it's actually data-driven, right? So you obtain some data.
Yeah, okay, in that sense, yes.
Have you evaluated some kind of sensitivity to the data? For example, suppose that you replace a sample, or that you have more data.
Okay.
I think it's statistical learning. It's called stability of learning algorithms.
Okay.
So I think it might also be interesting. I don't know if you have done
that. That's definitely very interesting. I'm wondering, just right off the cuff, I haven't given any thoughts a priori, but I'm wondering right off the cuff whether this can be measured considering how when you increase the coalition and you bring more players into the coalition, what happens to the value of the coalition? So you have some monotonicity. So in this case,
I'm not sure. I guess that at the end of the day, if you replace, there are some guarantees that are with high confidence. If you replace some data and you try to evaluate the sensitivity.
Okay.
But I'm not sure how it would play out in a coalitional game setting. I know in non-cooperative games, but I haven't tried it for coalitional.
Okay. That's definitely a good point.
My question builds a bit on yours. So my feeling is that a higher variance would help forming good coalitions. It's like, because you're aggregating, so if there is large uncertainty, then by aggregating we can bail each other out, right? That's just
that's true.
So are there two, let's say, competing forces here that we want high variance, but then this would lead to slower convergence?
Okay. I agree. So both elements are, I think, slower convergence comes with this term here, and I agree also on your first comment. I agree on both comments. The benefit of staying together increases when we face higher uncertainties, because if we are facing deterministic processes, then we can play alone. There's no benefit from aggregating, and that's an issue in wind production, because the benefit is if the wind is very uncorrelated and different between different wind farms, but then the wind farms need to be very far from each other, but they cannot bid on the same bus. They cannot operate on the same bus. So there are some technicalities that make the results not directly implementable, but science comes first before regulations. Okay, so we can try to convince policymakers that there might be a way to bring people from different regions together. But that's definitely a point.
Yes. Yeah. So if you consider, as you said, like open system, people come in and come out, I suspect again this optimizer X star will change. So your analysis would break?
People come in, come out, you have different indices, because J means for a given coalition.
Right, but so suppose that if this X star change, X star J change, right? So if you have a time varying dynamics,
okay.
So that this X star is not the same, so you have to at different time instances you may have different X stars.
Look, the optimum is calculated at steady state, so the optimum doesn't depend on time. It's the optimum.
If it were depending on time.
Oh, that's another story. So that means, but then the model at the beginning is different. When even this, because here there is no time. So
right.
If you analyze the X star is just the optimum of this objective function. If the optimum changes, that's a good point. I don't know. I mean, I haven't considered this, but it means you have to solve this problem every time you have an update, because you don't get just one optimum.
Right.
So that's a good point, but okay.
Because you have now an algorithm, I wonder whether you could track something. Things change.
Okay.
Maybe you don't know it's changing, but I don't know.
At the moment, it's just a regulation problem, so you
right.
want to get there.
Absolutely.
But that's a very good point. So what if you have a tracking signal? So right. This guy, yeah, okay. Next paper is going to be on this. Thanks for
the idea.
Yeah, thanks for that. I will acknowledge. I'm joking.
There was another question.
Oh yeah, okay. Suppose you have a particular computational time, so you don't have all the resources to compute the star accurately.
X star.
Exactly.
Okay.
Yeah. So do we know a bound for which, for example, I can say, okay, with this accuracy I need so many iterations, or the other way around?
Well, for the algorithm, you don't need to know X star. We calculate X star a priori to show that the algorithm will converge, but the grid algorithm doesn't need to know X star, the tracking point.
About U star, it converges at the end, right? So it converges after many iterations. You find the equilibrium, right?
Yes. Okay.
So suppose that you have k iterations and
okay.
you have not been at the equilibrium yet.
Okay.
Do we have a bound on the distance between these two? Like the approximate solution?
Is this bound here? I don't know, this.
Yeah, it might come from this. Yeah, okay.
Is it something that we can obtain from
just
for a specific time?
Yeah.
So for a given t. So you know that this deviation is upper bounded.
I guess you need the initial.
Yeah, you need information about where you start from.
Yes.